bit behind. This is BGP multi-homing techniques tutorial. Those of you who have been following the NANOG tutorials will probably notice I've been doing a few of these BGP tutorials. So this one follows on from the introductory tutorial that I gave at the last NANOG. So it starts introducing the concept of multi-homing, why we do it, how we do it, how we do some more of the finer parts of connecting our networks to other networks. My name is Philip Smith. I work with Cisco Systems. I live in Brisbane in Australia. I spend most of my time actually working around the Asia Pacific region. Sometimes come to North America, sometimes come to Europe, sometimes go to Africa, sometimes go to pretty much everywhere on the planet. But as I say, I do spend most of my time in Asia Pacific. So a lot of the work that you see in the tutorial here has come from real life experiences, both with the service providers I'm working with in my part of the world, and also from my time when I used to work at UUNet, running UUNet's UK network in those days, many years ago. So, presentation slides, wow, we can see the colors. Presentation slides are pretty much in the usual place, ftpeng.cisco.com/pfs/seminars, and just look for the NANOG 32 title there. I'll put this up again at the end of the presentation, so if you can't get it all down, then you get another chance at the end. I've put in quite a lot of configuration examples with the presentation. They all use Cisco IOS CLI. Hopefully you can understand that. If you don't, my apologies, but trust me, it's not really too hard. If there's anything that doesn't make sense, feel free to drop me an email afterwards or come ask me afterwards what might the issue be. But as I say, I've put configuration examples in there because a lot of the people who sit through the tutorials here at NANOG and in other operator forums around the world find it quite useful to compare what's put up here as a real live working example versus what they've actually got on their own routers. So the configuration examples are here. Hopefully they are of some use as well. The tutorial is aimed at service providers. That's not saying that people who run enterprise networks shouldn't come here, because a lot of useful techniques also for enterprises also. But it's primarily aimed at service providers, network operators and so forth. I'd also like to encourage you to ask questions, but if you want to ask questions, please use the microphones. The session is being recorded, so for those of people who can't actually be here at this time, you can look at the recording later on. So if you're going to ask questions, please use the microphones and announce your name and affiliation just so we know who you are. So we're going to try and get through all this in the two sessions that we have. The first 90 minutes will probably cover the first 4 bullets there. Why we go about multi-homing, what the definitions are, what some of the options are, how we go about preparing the network, and looking at some of the basic techniques to get going. And then in the second session, later this afternoon after the break, we'll have a look at slightly more complex scenarios, how we go about using communities, and if there's time, I'll throw in a small case study right at the end. Okay, so why do we multi-home? Well, it's all about getting redundancy, diversity, and reliability for your own network. That's the whole point of doing it. And if you're just connected to a single service provider, how your network appears on the internet and how it performs on the internet and the connectivity that you have is completely dependent on what your service provider is doing. When you're sitting at home on the end of a dial-up connection or a broadband connection, if your service provider disappears, you have no network connection, unless you have some other account with some other provider. So you're dependent really on the upstream provider. You're dependent on your local router, whether it's the configuration of the router, software on it, or the actual hardware itself. You're dependent on the connection between you and your upstream service provider, whether it's DSL or it's wireless or good old dial-up or traditional leased line. If there's any physical failure on the point-to-point connection, or there's some failure of the intermediate carrier, then you lose connectivity. And of course, your upstream service provider could have a bad hair day as well. Something could go wrong. They might do unscheduled maintenance in the middle of the day when you're doing your most important work, and so forth. Again, there can be any issues there. It's also reliability. Business critical applications demand continuous availability. And if you're trying to run a small business, medium business, or a large business, downtime means the time that your customers can't get access to your network, can't get access to your server or services. If you're selling product, whatever, they can't get access to do this. In some companies, e-commerce is actually extremely important. I can mention my own employer, Cisco. Most of the products we sell are done through the Cisco website. And if that disappeared for even a few seconds, it means millions of dollars potential loss. So you kind of always want your internet connectivity to be there. The other one is supplier diversity. And many businesses these days demand supplier diversity as a matter of course. They no longer want to put all their eggs in one basket. Many years ago, certainly in the early 90s, it was fine just to get an internet connection to go and play with. But these days, you want to try and use as many, well, not as many suppliers, but certainly a variety of suppliers. You're not stuck with just one. So quite typically, you have an internet connection from 2 or more suppliers. They've got 2 or more diverse links to the providers. When I hear and see many stories of people who multi-home their networks, but they buy the copper from the same phone company. And the phone company has the problem, and bang, the multi-home connection breaks. So when I do say, I do mean 2 or more diverse wide area network paths. So even if one path breaks, you have connectivity through the other. Through 2 or more exit points, and also 2 or more international connections, certainly in the provider space. Probably less so here in North America, but more so in other parts of the world. Certainly in Asia, having 2 or more international connections is actually pretty important. And one thing, just I suppose it's a theme throughout the whole presentation, is the concept of 2 of everything. It's really important to many organizations that they have 2 of every description. There's another reason, well, I wouldn't say it's a real reason, but it's quite often quoted, and that's leverage. Playing one service provider off against another one. If you multi-home against, say, with 2 or 3 different ISPs, you have different service level offerings. You may get different bandwidth, you may get different customer support, and I've seen many ISPs who will say, when they do the bargaining for renewal of contract and so forth, they can use this to play one provider off against another one. And that's used quite effectively, certainly in many more developing parts of the world. So whether it's for service quality or service offerings or just general network availability, multi-homing is actually quite a good reason for doing this also. So, summary of all that, it's quite easy to demand multi-homing as a requirement of any network operation, or whether it's service provider or any enterprise or edge network. And I see many cases, I see many RFPs where people say, yes, network needs to multi-home, must multi-home, but people haven't really thought through what it actually means, what they need to do. It just seems to be some button, some configuration you can type in the router that says multi-home, and it happens. But in real life, it means a little bit more. It has an impact on your own network, it has an impact on the actual internet out there, and has an impact on you, because if you're not really completely familiar with BGP and what it all can do, then it's like, oh my gosh, something can go wrong, I can break something, or worst case, you think you can break the internet. So, let's have a look at some of the definitions. What does it all mean? Well, multi-homing, as far as I'm concerned, is where you've got more than one link external to your own network. Okay, so it could be 2 or more links to the same upstream ISP, or it could be 2 or more links to different ISPs. In both those cases, for me, are multi-homing. You've usually got 2 external facing routers. If you're multi-homing with just one router, the router breaks, you're dead. So that's not really a very useful situation. It's better to have 2 external facing routers. And if you really push it, 2 external facing routers with different external paths, with different power supplies, preferably in different racks, even in different rooms, even in different buildings, even better at different locations. Okay? You want to give yourself as much link and location and service provider redundancy as possible. You also need an autonomous system number. To use BGP, you need an AS number. You can get those from your upstream ISP, or you can get them from the regional internet registry. So with each registry region, it's a slightly different process that you have to go through, but generally you get your AS number from your upstream service provider or the RAR. So whether that's APNIC, ARIN, LACNIC, or the RIPE-N6C, you have a choice. It's necessary when you have links to more than one ISP or you're connected to an exchange point, or both. Okay. An AS number is a 16-bit integer, so it ranges from 1 to 65534. The first and the last AS number are reserved, and the final 1023 are private ASs, so they're only intended for private use. So about 64,000 public AS numbers at the moment. And as far as allocations go, we're around about 34,000 ASs have been distributed to the registries for distribution to service providers. So we're just over halfway used up. Private ASs can be used in several instances. For example, if an ISP's got customers that are multi-homed onto their own backbone, as per RFC 2270, which we'll look at a bit later on, there you can use a private AS number. Corporate network that has several regions, but most of the connections to the internet are in the core only. There you can use private ASs as well. The example could be that maybe the IS people will run the corporate network in the core, the main headquarters, but they give an AS number to each of the satellite offices, so they can delegate some of the local operation to the different satellite offices. That's a reasonable common application of a private AS number as well. As far as the internet's concerned, it's still one organization. You don't need to see the constituent pieces within the corporate network. And the third application, of course, could be within a BGP configuration. If you don't know what that is, don't worry about it. If you do, worry about it. Private ASs, of course, should not appear on the public internet. So, as with private address space, again, that should not appear on the public internet. So, in any BGP configuration, make sure that private ASs are stripped out from any of the announcements that are made to the public internet. Now, each vendor implementation has a command that does that. I've put up the Cisco example so that you can see. It's generally a good idea if you're setting up configuration templates for your different routers to put this in the eBGP configuration template so that it is always there. Now, when we configure a lot of policy, and obviously there are many different ways of doing policy configuration on the routers, and the vendors are all very good. They give you lots and lots of tools, different tools, and lots of handy documentation and lots of examples. And you read it all and you think, wow, I can do anything and everything, but what do I do? So what I'm going to try and do here, in certainly my examples that I'll show you, is stick to these 3 basic principles. To filter prefixes, I'm just going to use prefix lists. To filter AS numbers, we're just going to use what's called a filter list. And to apply policy, we're going to use a concept called route map. Now, route maps are a lot more powerful in Cisco iOS, and presumably on other platforms as well, than just applying policy. But I've seen people dive in with all this route map type configuration, and they do filtering of prefixes and AS paths and apply policy and get horribly confused. Once you're an expert at all this, then you can do that. But to start off, we're going to keep things nice and simple. We filter prefixes using the prefix list. To apply the policies, we're going to use the rat maps, and that keeps life simple. The policy tools that we have, well, local preference is probably the most powerful one. That will control outbound traffic flows in your network. If you remember from the BGP intro tutorial, if you came to the last one, you apply local preference to inbound routing announcements to mark, well, give priority to those that you want to prefer. So higher local preference means the more important path. So that will determine outbound traffic flows in the network. MED, or metric, lets you control inbound traffic flows, but only between you and your neighboring AS if you're multi-homed to your neighboring AS. Although there are various knobs and hacks that you can do to make it apply to different ASs. But generally a metric's got local scope only between you and your neighboring service provider, so it's not wildly useful. More useful one is AS path prepend. And that's got internet scope. In other words, if you apply a prepend to an outbound routing announcement, that will be mostly visible across the whole internet. And that will determine your inbound traffic flows into your network. Obviously, if you remember the BGP path selection, the shorter AS path is preferred over the longer AS path. And finally, communities. Communities are very, very powerful policy tools. I mean, they've been around for, must be getting on for 8 or 9 years now. I remember the days before communities very, very well, and trying to apply policy with BGP was, well, it was an interesting challenge. It certainly led to very, very complex and convoluted configurations. When communities came along, they made life substantially easier. And towards the end of the tutorial, we're going to have a look at some of the communities, how we use them, and what some service providers are actually using them for. Now, we're going to make some more assumptions here. When we originate prefixes, we're going to announce the address block that has been assigned. So if you've got an address block from the registry for your upstream ISP, you're going to announce that address block. And I think that's pretty much a given, or I've always assumed that this is pretty much a given. But I still come across so many service providers all around the world who just say, I got 16 class Cs from whoever. And people are still thinking of classical routing, even though that was obsoleted in 1994. So we're 10 years on from that. So the kind of expectation you get from the registries when you give the address space is, if you get a /20, you announce that /20. Because that's the address chunk that you've got. Indeed, these days the minimum registry allocation is a /21, unless you're in Africa where I think it's a 22. And actually several ISPs will filter on this registry boundary. So if you announce a 24 out of what should be a 21 minimum allocation, it won't be visible within those ISPs' networks. And several ISPs also filter the rest of address space according to the IANA assignments. So they would do things like, 128.0/16 all the way through to wherever. Those used to be class B, so I'm going to filter on the /16 boundary. There's some people that will do that. And that activity, I've heard people call it net police. So be aware that some ISPs do that. I mean, I don't have any definitive list, but I keep bumping into the different ISPs every now and then. The registries will publish the minimum allocation sizes. So those are the URLs I've found. I have no idea where LACNIC publishes their one. I haven't found anything on the website yet, but I know they do have a minimum allocation size. IANA also publishes the address space that is assigned to N sites and allocated to RIRs, so that's public information. And several ISPs will actually use this to filter prefixes. So that's just a thing to bear in mind when you come to do the multi-homing thing, because you can't simply take whatever address space you've got and spray /24s out onto the internet. And last I looked, a few days ago, there are almost 80,000 /24s out there. And most of those come from ISPs who just take, I got my /20 from whoever, and they announce it as /24s. They don't even announce a covering aggregate. just send out the 20 filters. The main issue that I have with the whole net please prefix list is it makes multi-homing hard, or makes it harder to do, especially more towards the internet edge. Certainly in regions where they can't put the backbones together very easily, where domestic backbones are unavailable or cost a fortune compared with international bandwidth. And in many developing parts of the internet that still have issues with some of these filtering. They get highly suboptimal routing because of ISPs more on the core than internet filtering on the registry boundaries. And also we see emails from Rob Thomas and other people saying, please, please, please do this, and so forth. Or when the registries announced the new net block that they're going to start handling an address-based block. And many months pass and we still hear stories of ISPs filtering such and such /8 because, well, whoever set it up on the border router set it up and then decided to retire or leave. And the new people who have taken over don't understand the filters, too afraid to touch them in case they break the internet or break the network. So doing this filtering, it's actually quite a serious issue that people need to think about. Don't do it unless you're prepared to maintain it and understand some of the consequences. Okay, so I'll revisit some of the filtering bit a little bit later on in the piece, but that's just some of the early be aware things that when we do some of the multi-homing here, you're going to run into some of the filtering issues at some stage through your life. Now, some of the actual scenarios. We're going to look at these four. If you have a stub network like this, for example, you're AS101 and you've got two connections to AS100, but they're basically parallel circuits connecting from your border router to your upstream. There's actually no need for BGP in this situation. You're not really doing a multi-homing. All you're doing is having two parallel circuits. And the router will quite happily load share on these two parallel circuits. Just point a static default route to the upstream and life is good. I mean, you can run BGP on this if you really want to, but if you go to your upstream ISP and say, hey, I want an AS number for this, they'll say, nah. Okay? Because there's no need to do it. And it's unlikely for an upstream to actually give you an AS number or even try and run BGP in a situation like this. Note that's going from your router to their router, parallel circuits, because the router will quite happily load share on the static connections here. If you get a situation like this, where the two circuits leave your own router and go to different routers in your upstream ISP, whether it's in the same point of presence or going to a different point of presence, then you should use BGP. I mean, I've seen some people sit down and say, ooh, I can run OSPF on this, or ISIs, or even RIP. Yes, I have seen it. And I mean, those are internal routing protocols, and my definition of internal means inside. And if you're running a routing protocol outside your network, which is an inside routing protocol, that seems to not make much sense. But people do this. And I mean, I've seen lots of accidents, obviously. ISPs run OSPF, the customer runs OSPF. They leak their routes into each other's networks and don't understand what's going wrong. So try and avoid using an IGP for this type of multi-homing. BGP's there, it's nice and simple. We've got a few examples coming a bit later on. You see it's actually really easy to configure. In this case, use a private AS number, because this situation is nothing different as far as the internet's concerned. As far as the internet's concerned, you're just a customer of AS100. The internet doesn't see the detail of the connection between you and the AS100 service provider. Okay, so you don't need to use a public AS number to make a distinction in policy. So private AS number works fine. Talk to your upstream which private AS number you can use, or they may just tell you which one to use, and off you go. When you get into the more detailed situation of, say, a multi-home network like this, then, well, there are many, many situations possible here. You need a public AS number, obviously. You can have multiple sessions to same ISP, for example, from AS100 to AS200. So that could be a load balancing situation, as we had in the previous slide. You could have a backup through another AS300 could provide the backup situation, or you want to maybe load share between your primary and your secondary and do other various selection things. Like, this is a little bit more complicated situation, but this is actually more real life. This is what people are actually trying to do. And there's no magic button you can do, say, on AS100, say, I want to multi-home and load share and everything to be perfect. It would be great if there was, because then I wouldn't need to give the tutorial up here, and it would make life so much easier also. Now let's look at some detailed examples. Say you've got multiple sessions to a single service provider. Now I said before, well, you can run static routes if you want to. That works perfectly well. However, if you take an example, say in the previous slide, where you need to talk BGP because you've got more than one link to different POPs or different routers in that service provider network, but one of these links may be with multiple circuits, and you need to use BGP. Well, here you can use what's called eBGP multi-hop. So what you do is you run BGP between the loopback interfaces of the neighboring routers. You point static routes to reach the loopbacks, and then the BGPs will actually load share over these three parallel circuits. So here's one particular example. Pardon me. You have the eBGP multi-hop configuration line. The number 2 there refers to the number of TTL hops that you're going to go through, so it goes from loopback to router to the remote loopback. And then you simply point static routes to the remote loopback over each of the serial interfaces, and that will allow the router to actually load share. Okay. So this is if you need to use BGP over the parallel connections like this. I generally dislike eBGP multi-hop quite intensely. It's partly from, I suppose, my past experience working for an ISP and my current experience trying to help customers and service providers untangle themselves from messes caused by eBGP multi-hop. So I generally say use eBGP multi-hop if you absolutely need to. So for example, if you're providing, say, a data feed to service providers, for example, the route views system, University of Oregon, that's provided by eBGP multi-hop from all around the world. And various other view systems around the world operate like this. Or if you're load sharing across multiple links, their eBGP multi-hop is quite handy, because it will let you run a single BGP session over multiple parallel circuits. Many ISPs actually discourage its use. In fact, some ISPs encourage its use, which I find quite bizarre given the quote that I have down there. That's actually from one of the big Tier 1 ISPs. And they're quite public and quite clear about it. They will do it, but they won't support it as a standard offering. So if you go and ask them nicely and often enough, they will actually configure it. Because they highlight the main issues, you end up with routing loops, because people set ridiculous time to lives, and they don't understand that, well, the BGP may still work, but that the link between the two networks may be down. So we see classic situations of, oh, well, the network's got very slow, but the BGP session's still up. Well, yes, because you're rerouting through your backup link, which goes halfway around the world. Oh, but how do you know it's down? Well, and so forth. The customer doesn't understand. They just simply phone up and say, ooh, the internet's got slow, your network's broken, type response. Okay, so some service providers are quite nervous about doing this. Yet, some other service providers, I find that they will only talk with eBGP multi-hop, because they've only got one router in the network that's taking all the eBGP sessions for their customers. And they don't do anything else. And of course, when that one router goes down, then all the eBGP customers break and so forth. But that's how people seem to end up designing things. So, as I say, try and avoid using eBGP multi-hop. I prefer the eBGP that's on the direct point-to-point connection. Generally makes things easier. So another thing that is available in some implementations is this BGP multipath concept, where BGP will actually install multiple paths in the forwarding table. Now here you can have a limit of a number of parallel paths depending on the implementation. It can be 6 on some routers, 8 on some routers, more on even others. But what you'd end up doing here, say in the 3 connections we have, you'd end up running 3 eBGP sessions, which is fine, but if you're carrying the full routing table on these, between these 2 autonomous systems, getting 150,000 prefixes on 3 eBGP sessions means almost 500,000 paths, which can mean a lot of memory, can mean a lot of CPU, and in general hard to manage. So this is kind of out of favour, certainly for major links between, well, certainly major peering links between service providers. The general situation that you find for most multi-homing is something like this, where people are actually going for the redundancy. They have parallel paths from different routers, maybe to different locations, more than likely to different occasions. And you can't use any sort of really simple construct. You've got to work a little bit harder to try and set up a multi-homing group. And it's always interesting looking at how people approach this. It seems to be a thing that in people's heads that BGP is really, really complicated. I mean, I agree, it probably can be. And there's some certainly amazing configurations and amazing experts out there who can completely baffle everybody with science. But the way to try and start up any of this is to keep it really, really simple. So as I say in the first point here, the simplest scheme is to use the defaults. Okay, start with nothing, work upwards. It's a lot easier than starting with everything and complexity and then trying to work down. Try and learn and advertise prefixes for better control. You need a little bit of planning and a little bit of work to actually achieve what you want. So for example, point default towards one ISP, learn selected prefixes from another ISP, modify this number until you've learnt something that will give you acceptable load balancing. But there isn't any magic solution. Okay, there's no router BGP auto multi-home, unfortunately. Okay, so in this slide really summarizes the whole thing that I'm going to try and do with this whole presentation. I'm not going to stand up here and give you fantastically complex scenarios, because I find that trying to explain them to relative newcomers to BGP would just glaze over and go, maybe I should have taken up some other vocation or something rather than doing this internet thing. So what I'm trying to do is to start with something really nice and simple, show you how you can build on that. Once you learn the simple stuff, doing the more complicated scenarios actually becomes much simpler. Before we get into some of the real detail, let's have a look at preparing the network. Again, a lot of people who want to multi-home for the first time probably have a nice simple network that's maybe even got nothing more than static routing. Or maybe they're running just an internal routing protocol, maybe nothing more than OSPF. So you want to try and deploy BGP on this so you can actually head off and multi-home. Well, if you're going to use BGP, you need your AS number. So go apply for that. Go to your upstream ISP, they should be able to get one for you. Join a registry if you aren't a member of one of those, get an AS number from them. Some registries will give you one-off assignments of AS numbers. It's generally pretty easy to do. If you're multi-homing to different ISPs, of course, you need the public AS number. If you're just going to multi-home to the same ISP, talk to them about using a private AS number. If you go to a registry and say, oh, I'm only going to multi-home to such and such, they'll tell you politely, hopefully, to go away. Because public AS number is only given if you connect to 2 different networks. I'm going to look at 2 examples. The first example is where the network is only running static routes. The second example is where the network is running an IGP. Okay, so we've only got static routes. So we've got a small network, it's all statically routed, pointing into the core, pointing to the edge, and the static route pointing to the upstream. So upstream ISP is announcing our prefix for us. We want to multi-home this network. What do we do? Well, we need to make a decision on which IGP to use. deciding on IGP, well, it's simple toss-up between OSPF and ISIS. That's completely out of the scope of here. There's been enough NANOG presentations and tutorials and so forth about the merits of OSPF and ISIS. They're pretty much the same anyway, apart from the actual detail. So whichever one you're happier with, go pick that. Second step is to assign loopback interfaces and /32 addresses for each router that will run the IGP. Loopback is generally used for, in some cases, for OSPF, for the router ID. It can be used as the BGP router ID. It's handy for running the IBGP between as well. It's quite a useful interface and therefore concept to have within each router on the network. Okay, so we set up all the loopbacks, and that way we can get OSPF and BGP up and running. We then go and deploy IGP. Generally that should be pretty simple to try and do. You can deploy an IGP with no impact on the existing static routing. Okay, static routing generally has a much higher priority over any dynamic routing protocol. For example, in iOS, static route distance is 1, OSPF distance is 110. So you can set up everything in OSPF and the static routes will still take priority. And I've given this presentation a few other places and people go, I don't believe you. And it's like, okay, I'll show you. I've done quite a few networks where I've set up OSPF completely across the network in the middle of the day and it's had no impact whatsoever. Where you have the impact is pulling out the static routes. You do that during the maintenance period. But actually deploying OSPF has been no issue at all. Because of course the smallest distance wins. Static route will always take priority. I'm not going to try and sort of spend time teaching deployment of an IGP, but the important thing of course is to keep the link state database lean. In other words, keep the number of prefixes in the interior routing protocol as small as possible. The smaller it is, the faster the convergence, the faster the network can handle with breaks. So for example, the router loopbacks will go in the IGP, the WAN point-to-point links will go in the IGP. In fact, any link where there's an IGP dynamic routing running should go in the IGP. The rest will go into BGP. Summarization, if it's possible, if you're clever with the addressing plan, you can do some summarization, so that all helps too. So routes which don't go into the IGP include dynamic assignment pools, for example DSL, cable, DAL, customer point-to-point link addressing. Got 10,000 customers, you don't want 10,000 /30s in your IGP because that makes your IGP big. So you can use things like next hop south, that's one way to get around it, or you can stick all your /30s into your IBGP if you need reachability for those too. Static or hosting LANs, don't put those into IGP because they're just static networks. Customer assigned address space, obviously you've got your own address blocks, you're going to give some to your customers for them to use, don't put that in your IGP. I think probably the biggest IGPs I've seen before serious network problems have happened have been about 15 to 20,000 prefixes. And then you've had really serious issues. Like recovery times of 5 minutes or so if networks break. And you really want to try and avoid that. You want your IGP to have pretty much instant response for any network problems. So don't put customer address space into IGP. BGP is a wonderful load pad. You can put any amount of junk into BGP and quite happily carry that around in the network. And anything else you can think of that I didn't mention in the previous slide. I think you've got everything here. And now the second step is to configure the local network to use IBGP. Remember, you've still got your static routes there, so you can still configure IBGP and not break anything. IBGP can run on all the routers in your backbone if you want to. It can run on a subset of routers or just on the upstream edge. Again, that's a choice that you can make. The important thing is IBGP must run on all the routers in the transit path between the external connections. So for example, in this picture, it's not a good example, you have to run IBGP on all the routers here. If the link broke between A and B, then the backup might be ADCB. And if you didn't run iBGP and router D won't have much idea of where the exit for the network is. Or the only idea it has is the exit goes back to A. So if A tries to get to an exit path that's reached through B, you'd end up with an oscillation of traffic between router A and B. So that's not very useful. If you have a situation like this, you only need to run iBGP on routers A, B, and D, because C, E, and F are on the edge of the network. Okay, they're not in any possible transit path between A and B. Okay. Now, typical service provider networks will have 3 layers. The core network, that's what it generally is the backbone, or what I would call the transit path in the network. There's a distribution layer, some networks have these. It's the middle part of the network. It's the point of present aggregation layer. If you've got lots of, say, leaf sites or leaf networks, regional networks that you connect into your core, you connect them into a distribution layer. And then, of course, the aggregation layer is where you connect the customers. So all your different aggregation routers, your different classes of routers, the aggregation devices would be here. Say most medium-sized networks would probably have a core and aggregation. It's only the large networks that would have a distribution layer as well. And you really need to consider where you need to run iBGP in all of this. Most ISPs just say, well, I'll keep life simple, I'll just run it on everything. Because then I've got a complete idea of what my network looks like. It saves the complexity later on. But for aggregation layer, iBGP is optional. In fact, some aggregation devices can't run anything apart from RIP usually. So you can't run iBGP on these, obviously. We're trying to run maybe iBGP and aggregation layer. If all your devices support it, maybe it makes sense. As I say, many ISPs seem to be running iBGP here, usually partial routing rather than carrying the full routing table. What all these routers need to know is how to get to the rest of the customers within the network, and maybe a default route as well that will get me somewhere towards the core so I know how to get outside the backbone. Full routing isn't really needed unless the customers want the full routing table. And then again, they tend to set aside one router that carries a full routing table for any customers that seem to want 150,000 prefixes. But as I say, partial routing is generally cheaper and easier to do. Usually, as I say, some internal prefixes, and maybe a default to get to the core, and maybe some external prefixes if there's any strange multi-homing that's required. This is actually easier to implement than it sounds describing it. Using BGP communities and any of the peer templates makes this quite simple to do. If you set up all your internal prefixes in one community and your external prefix in another community, it's a very simple filter simply to apply this so that your aggregation routers only view the prefixes belonging to one community. Many aggregation devices can't run iBGP, as I said. Rather than using OSPF for them and putting all the customers into OSPF and then distributing OSPF into BGP, that's just ugly and messy. I'd rather use a static route from this aggregation device pointed to something that can actually run BGP and go straight through that way, rather than using intermediate internal routing protocol step. You'd still use an IGP for best exits, so do something like inject a default route into the IGP, and then you have your best exit that way. Distribution layer. Virtually every network I've seen is running iBGP in the distribution layer. Whether you use full routing or partial routing is another issue. With the routing table getting bigger and bigger all the time, more ISPs are using partial routing. So it could be their own backbone address space and the neighboring AS's address space, but not prefixes from other parts of the world. It doesn't have to run iBGP, but I really wouldn't encourage you to go down that path. Some people use IGP to carry the customer prefixes, but this simply doesn't scale, as I've said before. And really my third point there is the point I want to make. Networks which plan to grow large should deploy iBGP from day one. And that's my encouragement. If you just want to run a small toy network, then don't bother with any of this. But you're going to grow your network bigger as time goes by, so try and deploy what you're going to do in 2 or 3 years' time. Because redesigning or reconfiguring your network is pretty painful. So as I say, try and start off with IBGP from the first. The core network is usually the transit path, so your core network will be all your backbone routers, your border routers, so forth. You need IBGP here. Full routing table is pretty common, certainly for most service providers that are providing transit to other ISPs. You can get away with partial routes if you're not an actual transit provider. So that should be fairly straightforward to do. Decide on what the best BGP policy is for you. Full routes everywhere, partial routes everywhere, or a mixture, cascading mixture as I've just described. My general preference and recommendation is always try and run IBGP and everything. It's easier to filter the IBGP session using the communities that you've set up than trying to set up one policy one day and then 6 months later when your salespeople decide to sell a new service that they tell you about 10 minutes before the customer's meant to be delivered, that you've got to reconfigure your network. It's generally easier to set it all up as you intended to grow for the long term. Also, you need to consider IBGP scaling technique. We covered that in the intro tutorial. What your community policy is going to be. It's worth spending time to come up with a decent policy on what your community is going to be. So in the second section of this tutorial, I'm going to show you some of the communities that other service providers are using. I mean, there's no fixed rules about what should and shouldn't be used for communities, but if you take your ideas from what other ISPs have done, you can come up with some pretty good policies on your own. How are you going to scale your IBGP? Are you going to use route reflectors? Are you going to use BGP confederation? And then you need to consider some, well, I suppose, techniques which would make life easier for you. For example, peer groups, peer templates, or whatever your favorite vendor has to make the configuration simpler. And then you deploy IBGP. And there's really not much more than that. First step, introduce the IBGP mesh on the chosen routers. Make sure the IBGP distance is greater than the IGP distance. And it is in most cases, but it's worth checking. Install the customer prefixes into IBGP. Now notice, remember, we're still considering the first example where everything is set up with static routes. You've got your core router, it's pointing static routes to your aggregation routers, which have static routes pointing to your customers. So you can deploy OSPF and IBGP without breaking anything. Okay, so you put your customer prefixes into IBGP. Make sure the network still works. Step 3 is the biggie, because that's where you're going to remove the static routing for the prefixes which are now in the IGP and the IBGP. So the first thing you might want to do is say pull out some of your customer static routes, pull those out. You do this during a maintenance slot, obviously. You don't want to do it in the middle of the day. The last thing you want to do, if you've done something wrong, is your customer to phone you up and start shouting at you. So do it during a maintenance period. Pull the static route out. The IBGP entry should take over. And check that it does and that you've got reachability for your customers and so forth. Okay. And that's it. That is the IBGP and the IGP deploy. And looking at it, it's probably a lot of words. And it probably sound a little bit more complicated than it might be. But I've actually presented these slides to a lot of ISPs who have had nothing more than static routes within their own networks. They've had to deploy BGP, and they've actually been able to work through this and succeed, and without actually much complication at all. Simply relying on the fact that the static route distance is so much smaller than OSPF and the BGP distance. What does install customer prefixes into IBGP actually mean? Now this means customer assigned address space. It means everything on that slide that I talked about a few slides ago. So we set up the network statement for BGP, we set up the static route, to make sure the entry is in the routing table as well. We set up any communities that we're going to use to make sure we have a unique community for to identify the customer assignments. We have different classes of customers, so we set up the communities that you want to use there. The customer-facing point-to-point links. If you need reachability to your customer point-to-point links, you may be running a network management system, don't put the customer point-to-point links in your IGP, put them into IBGP. But don't announce these /30s out to the internet. You could do things like maybe redistribute these connected links through filters, which only allow the point-to-point links into IBGP. That works fine. And use a unique community to identify those as well, so that you can filter them out at the edge of the network. Or maybe you only want to set up an IBGP that will only speak to your monitoring system part of the network. Other customer prefixes could be dynamic assignment pools for broadband, home users, dial-up and so forth, and any local area networks as well. So you can be hosting networks, your own services, and so forth. Again, you may want to set aside a unique community to identify these networks. What do I mean by carefully removing static routes? I don't mean setting up a script on a Unix system that automatically logs into every route and removes all the statics it can find. You really need to work on one router at a time, pulling them out one at a time. Okay, go to one router, pick on one customer, take out the static route. Can you still reach the customer? If not, try and figure out why not. Okay. Once you're happy with that one, try the next one, and so on, and just step through it carefully. Once you've figured out any teething problems, you can maybe do a router at a time and take out all the static routes there for customer connections. I suppose the other thing to remember is what I say in the brackets here. Remember to look in the routing table. Don't look in the forwarding table. It's very important to look in the routing table. Do the next router. Then you work through until you've done the whole point of presence. Once the whole point of presence is done, probably have a break. Wait a week. See if there's any feedback, adverse or otherwise. Then go and move on to the next point of presence. Don't try and do this in all one big go. Again, it depends on the size of the network. I generally prefer to do a single installation per maintenance period. Okay. Now, the previous steps are all not flag-based steps. Okay, they all can be carried out during different maintenance periods. And I've said you can do some of the steps during the day. Now, why as a network operator wouldn't do that anyway? Even though it has no impact on any of the existing routing, it's still better only to work on the network during the maintenance periods. So step 1 could be done the first week, step 2 in the second week, step 3 in the third week, and so forth. And set up a nice phased approach to doing this. And if you've got proper planning, they should have no customer impact whatsoever. The second example, it's similar, but not quite the same. Here would be a service provider who's only running OSPF or ISIS at the moment. They put all their customers, in fact, they put everything into the interior routing protocol. They've discovered the interior routing protocol is getting slower and slower with the bigger number of prefixes in there. They've beaten up all the vendors to try and make the routers go faster, but they've finally given in and decided, oh well, maybe we should do what's actually common practice and use only the IGP for point-to-point links, and we'll put everything else into BGP. So what do they actually have to do? Okay, I'm assuming again we're only using OSPF and ISIs. RIP doesn't count as an interior routing protocol, not anymore. If it's not already done, we assign loopback interfaces and all the /32s that go with them. So remember we set up a loopback so we can run IBGP between all the loopbacks. Make sure that these are actually appearing in the IGP that's chosen. Then we can set up IBGP. We go through the same decision process. Which part of the network? How much of the network? How many prefixes? Full routing table, partial routing table, or what? What's the community policy? What's the IBGP scaling we're going to use, and so forth. Make all those decisions, and then you should be able to go and deploy. First thing we do is introduce the IBGP mesh on the chosen routers. Make sure the IBGP distance is greater than IGP. So Cisco's default is 200 for IBGP, which is fair enough. That's a lot larger than the OSPF distance of 110. We then install the customer prefix into IBGP. Again, does the network all work? It should still all work because we still have the IGP there sitting at distance 110. We then reduce the BGP distance to be less than the IGP. And that's the scary step. Here you're making IBGP more important than OSPF. So all the customer prefixes that are in IBGP as well as in OSPF will now pick the preferred path to IBGP. Now you can remove those customer prefixes from the IGP. And the network should still all work because the priority is now given to IBGP. We then restore the BGP distance to be greater than IGP, and you can then go and do eBGP and so forth. So installing customer prefixes into IBGP, it's the same as we discussed before. It's exactly the same set of prefixes, pretty much everything apart from point-to-point links within your own backbone. Removing the customer routes. Well, you want to check that the IGP route for a particular destination is also learned by IBGP. So you look in the BGP table, as well as looking in the link state database of the routing protocol, and then have a look and see what's in the routing table. Okay. You change the distances around, check that the entry in the routing table has been caused by BGP, not by OSPF. Okay, so what you do is you work through the whole router until you get all these customers done. Once you're happy, move on to the next router. Once you finish the POP, move on to the next POP until it's all complete. And again, this technique has, I've helped several ISPs work through this technique, and they have managed to migrate from running IBGP only to an IBGP IGP overlay without really any major incidents whatsoever. I've put some configuration examples in here just for a change. The red is not so obvious, unfortunately, in this one, but I've added in the top there, interface loopback 0. We've created an interface, a loopback interface on the router. This is what we're going to use as the anchor for the IBGP within our backbone. It uses the OSPF router ID and a host of other things as well. And then within OSPF, we've got the network statement. We're not defining OSPF adjacencies, and the loopback. Otherwise, it's pretty much standard OSPF configuration that you would find on an ISP that only uses OSPF for everything. Okay. So the redistribute connected means they redistribute the point-to-point links for the customers into OSPF, and the redistribute static means they redistribute all the customer networks, customer assigned address space into OSPF. It's a very typical configuration. Now, we've now added the BGP configuration. Here the BGP distance is 200. So you notice the distance BGP is 200. That's how you configure it in iOS speak. It means that eBGP, IBGP, and locally originated prefixes all have distance 200. We've got network statements for the customer. Those two network statements there are the two example customer assignments that I had on the previous slide. That will put them into BGP. And there's a static route pointing to the 00 and 001 for the two customers. We've got a neighbor statement. Well, that's another IBGP speaker, for example, just to show what it's like. And then I've got the first line. I've got a redistribute connected subnets right map point to point. Now, what this does, remember I was redistributing the customer point-to-point links into OSPF. Well, we want to take the customer point-to-point links out of OSPF and put them into IBGP, because we're running a monitoring system that monitors the point-to-point links to all our customers, so we can let our customers know if the link goes down. So that redistribute command up at the top there will take the customer point-to-point links and put them into IBGP. The route map is there really to make sure that we only put point-to-point links. So match IP address 1. For access list 1 there lists the address block that we're going to use for all our customer point-to-point links. So that means that we're going to redistribute all the address well, all the prefixes we see in that address block into BGP, and we're going to set the community 100:1. And that community tells you that this is a point-to-point link. So you'd apply it at your filters elsewhere in the network. There are quite a few ISPs who do this type of thing because they need to monitor their customer connections. And I watch the routing table, as some of you probably know. I post a weekly routing report to the NANOG mailing list amongst lots of other places. And from time to time, if you actually have a look, you see that there are providers who will leak /30s, the actual IBGP /30s out into the global internet. And that's usually caused by a community filter somewhere breaking. So that's the type of configuration you do. You've now moved your customer point-to-point connections into the BGP. So that's steps 1 and 2 previously. Now step 3 and 4, notice I've removed the OSPF redistribution. Because my customer address space and the point-to-point links are now in BGP, I don't have to put them into OSPF. So this is the scary step, if you like. This is where you're yanking a whole lot of prefixes out of OSPF and relying on BGP only. So I've removed the redistribution that was done to put them into OSPF. And notice also I've reduced the BGP distance. BGP distance is now 20. It takes priority over OSPF. So that you do that, I think that was step 3, and then step 4 is removing the redistribution. Okay. So IBGP distance 20 means that prefixes in IBGP take priority over prefixes in OSPF. And then finally step 5, the only change here is the distance. We push it back to 200 again. We always want the BGP distance to be greater than the IGP distance. If you don't do that, you learn prefixes from outside your network that match prefixes inside your network. Guess who wins? You get an exact match. You learn your address space from outside. Well, you start doing a denial of service attack on your own network. I've been there, and that's happened to me by accident. So it's actually pretty important to make sure that your eBGP and IBGP distance is a lot higher than what you'd have for your IGP. Okay, so we'll put that back to 200. And that's it. Again, these previous steps aren't really major flag dates, but they should be done during the maintenance period. I suppose step 3 and 4 is the big one where you're removing the redistribution from OSPF. But again, on the networks that I've worked with where I've done this, it hasn't been much of a major incident at all. As long as you give enough time between each step, it just works. It just happens perfectly well. Again, there's no customer visible impact whatsoever. And I've helped networks come from 5,000 prefixes in the OSPF down to about 50. And the noticeable impact has been that, well, as far as the customer is concerned, nothing has changed, but failover within their own backbone has been instant, and the IBGP has scaled much, much better. Okay, so summary of all that. We've got the essential networks within IGP, so anything that's important for the IGP, in other words, point-to-point links, are in there. Everything else has gone into IBGP. IBGP is like the common carrier. You can put all sorts of junk in there, and it will carry it quite happily. You've deployed IBGP across the backbone, whether you've done full or partial or upstream edge only, it's up to you. BGP distance is greater than any IGP, which is fine, so you're now ready to deploy eBGP. And that takes us on to the basic multi-homing part. Right, now I've called this basic multi-homing really to try and emphasize the point that we want to try and learn to walk before we try running. People who have come to multi-homing the first time, some of the questions I've seen asked on, say, ISP, BGP and so forth, they're like, oh, I'm a newcomer to BGP and I need to do this, and they post some amazingly convoluted configuration that I can't imagine where they've got from. And it's people trying to do really, really complex stuff, and they have such simple situations that they're trying to start off with. So generally when I tend to give private responses to some of the people who come asking for help, and it's like, well, why do you need to do this? What's wrong with doing it this way and this way and this way? And it's usually enough for most people to look at some of the simple techniques. So it's no frills multi-homing. We're going to look at two cases, multi-homing with the same ISP, because there's a reasonable amount of that happening, and we'll have a look at multi-homing to different ISPs. I'm going to keep these examples nice and easy, because I think if you can understand easy concepts, then you can make the more complex scenarios easier to understand. And after the break, we're going to look at more complex ones. So this is just a nice easy start. After the break, it's going to get slightly more complex. But the basic multi-homing is most commonplace at the edge of the internet. So it can be a small business, it can be a small service provider. They've got the business up and running, the connection up and running. They want it to be slightly more reliable. They don't want to be at the vagaries of the service provider. So they want to have a little bit more reliability on the network. Now the networks here really only care about inbound traffic flow. You think about it. Most of your customers, if you're an edge provider on the internet, what do? They're dialing up, or they're using broadband, and they're browsing the internet. It's web and email. And web is pretty much send a request out, get a huge amount of data in. Email, generally huge amount of data in. So these networks are generally only concerned with inbound traffic flows, because outbound traffic flows maybe 20% of the total volume. So it doesn't really matter where it goes. It doesn't matter so much. And nearest exit routing is usually fine. It's usually fine for most people. Then again, okay, there's some situations where it's not good enough. There's some providers I've worked with who've got satellite connections, and one link goes to Europe, the other link comes here to the US, and it's like trying to multi-home between those two is entertaining. So for those, it needs something slightly more special. But in the general case, where you're multi-homing between service providers in the same region, nearest exit is good enough. Now, for multi-homing to the same ISP, we can use a private AS number. That's fairly standard. Talk to your upstream, they will give you one. If they don't really know what you're talking about, you can tell them which private one that you're going to use. And I've seen both situations. There's no need for a public AS number, and there's no justification for one either. You won't get one from the registries. Because making the nets of this end site visible gives no useful information to the internet. Because all that everybody sees is simply your AS number sitting behind somebody else's, and there's no path to diversity information there at all. The upstream ISP will simply proxy aggregates, or he will announce your prefix, or to look as though he's announcing your prefix on your behalf. He announces your address plot to the internet from their AS, as though you would have done if you simply had a static connection. Right? This type of multi-homing lets you load share between you and your upstream ISP. The rest of the internet doesn't need to know about it, doesn't care about it. Okay, so first example, two links to the same ISP. We've got one link as the primary, the other link is the backup. This applies when a site has bought a large primary WAN connection to their upstream service provider and a small secondary link as the backup. For example, primary path might be an E1 or T1 or whatever, and they back it up with 64K, 56, whatever. I've just picked some numbers as examples. Trying to pick numbers that work in every economy is always a challenge, so just pick some numbers. 2 megabit circuit versus 64K. I mean, it's not such a usual situation these days, but there's still some people who will go down this particular path. The picture could be like this. Routers A and B are in the private AS 65534. C and D are in the service provider. The primary path is between A and C, the backup path is between B and D. Router E does all the proxy aggregation, whatever you like, removes the private AS before the announcement to the internet. So what do we do here? Well, we said we're going to assume a /19 aggregate for all the networks, all the examples throughout the presentation, just for the sake of argument. So what we're going to do is, on the primary path, we're going to announce the /19 outbound. Inbound, we're just going to receive the default route. The backup link, we're going to announce the /19 with an increased metric. Now if you remember, lowest metric wins in BGP. So metric of 0 is preferred over a metric of 200. So if you send a prefix on the primary path with, say, a metric of 0, and on the backup path with a metric of 100, then the primary path is the one that's preferred, because metric 100 is less important than metric of 0. What about inbound? Well, you receive the default route also on the backup link, but this time you reduce the local preference. Default local preference, again, depends on the implementation, could be 100. So if you reduce the local preference, it means it's less important, so this becomes the actual backup. When one link fails, well, you're announcing the /19 out of both links. So even if one link fails, you still get the announcement out the other way, which means traffic comes in the other way. You're hearing the default route through both links coming in, so even if one link breaks, you get the backup through the default the other way. So it's a very, very simple setup. And here's the configuration. So you're sitting in AS65534, you've got your address block there, the /19, prefix list, aggregate out, so your outbound filter is ascend only your aggregate block. The aggregate block 121.10/19. Inbound, you only want to accept the default route from your upstream ISP, and you have the prefix filter set up there. And that's your configuration. You need to do nothing else. Okay, that's a nice simple start. You need to do the filtering. Don't ever assume that your upstream provider can do the filtering for you. I mean, yes, they will, sometimes. But if they break anything, accidents do happen, then you could end up with, well, who knows what appearing down there. So always do your own filtering. Never trust anybody else to do your filtering, even though they may well be doing it for you. Router B configuration is, well, router B is the backup path. So the configuration is going to be roughly the same, but not completely. So we've got the network statement again for our address block. We've got the neighbor statements, of course, remote AS100, prefix list aggregate out, same thing as last time, prefix list default in, same as on router A, but we're applying policy. So that's why we have two route maps. Router D out applies outbound policy. There we set a metric. We're setting a high metric. Router D in is where we're setting a low local preference. High metric out means we're going to tell the upstream that this is the backup path. It's going to be a higher metric than another one. Router D in route map, we're going to set a lower local preference. It tells our network that this is the backup path for outbound traffic. So we look at the route maps, and sure enough, router D out, if you send the aggregate out, we're setting metric to 10. 10 is higher than the default of 0, so this becomes a backup path. Inbound, we're setting the local preference 90. Why 90? Well, that's actually RFC 1998 example. I just used that just for consistency with that. We'll see it later. Okay, so that's the router B example. That provides the backup path. Okay, if the primary link between router A and router C breaks, this configuration will give us the exact backup. And of course, if this link breaks, then router A to C is still there as the primary path. Now, if we look on the upstream ISP, if we look on router C, well, here the service provider doesn't really need to do very much at all. He's got his private AS, peering, prefix list customer in, because he always filters what he hears from his customers. He can never trust his customers to actually send out the space that they say they have. And he's only ever going to send a default route out, uses the default originate command to actually do that. And what's really helpful for the upstream ISP is his configuration in other router is exactly the same. See that? There's no difference, apart from the addresses. So this gives a nice scaling path for the service provider. All he's doing is providing a BGP configuration to his customer. His customer can control how the BGP is actually set up. Customer is sending an MED to him. Customer is using local preference. So basically the customer has been given the tools. Now I certainly found that when we're running the network at UUNet that Customers are actually quite delighted to be given control over the multi-homing capability. And some of them didn't really like to be left with the, it's just a black magic type box thing that somebody can control and it all worked. A lot of them didn't really like that. They liked to be able to get in there and be able to change things. This was actually quite neat for them. We didn't have to worry about anything. We just set this up on our backbone routers, and we showed the customers what they had to do for the BGP multi-homing, what they could tweak and change, and left them to it. Of course, if they broke things, then they had to fix it. They couldn't blame us. Router E configuration, if you remember, that one was on the edge of AS100 that connected to the rest of the internet. And what this one does, notice the remove private AS configuration. Remove private AS strips out the private AS 65534 that the customer was using. Prefix list customer out, that will filter all the customer prefixes. So one will let our customer address space out, not any old thing. And that one works quite nicely on the board of the router. Obviously, if there are more customers, this is going to be a more substantial configuration, but that shows you the basic idea. So within AS100, we see AS65534 as the private AS, but for the rest of the internet, all we see is AS100 originating the prefix that came from AS65534. So that's quite a neat, simple configuration. As I was saying at the start of this one, it's not used so much these days. I mean, people don't tend to go and buy circuits and leave one completely unused. They tend to go and buy circuits and try and load balance between the two. So this is more common. Again, I'm going to start with an easy example. We're going to assume equal capacity circuits. That's a simple example we start with. As soon as the circuits get unequal capacity, then we've got to think a little bit harder. But this is like the first step. Okay, so link 1 is between routers A and C, link 2 is between routers B and D. Router E does what it did before in the previous example. We announced the /19 aggregate on each link because AS65534 has a /19 address block. We announced the aggregate on each link. We split the 19 and announced it as two 20s as well. We announced one /20 in one link, another /20 on the other link. Okay, so note this. Each link, we announce the /19. We always announce the aggregate. We then also split the 19 into two 20s. We announce one 20 on one link, another 20 on the other link. Now you know how IPv4 lookup is. It's longest match. Okay, so traffic for the first /20 will come in through one link. Traffic for the other /20 will come in through the other link. So you've got your first attempt at load balancing. Now we made a lot of assumptions here. We've assumed that the traffic coming in for each IP address is equal, which is rarely the case. But you have to try and start somewhere. And it's generally easier to start with something like this and then subdivide, rather than trying to say, oh my gosh, what am I going to do? I know what I can do. I used to remember these Class C things. Let's announce 32 Class Cs in this case and see what happens. Okay? Like, throw balls into the air and see how many I can catch. It generally doesn't work. If you trying to learn to juggle, take one at a time and add a second one and third one and so forth. Not throw all 10 into the air and see how many can hit you in the head. Okay, so we start with splitting into two /20s first and then see how we go. Let us say that vary the split until you get perfect load sharing. You might find that two /20s don't work. You might need a /20 and two /21s. And you're 20 and a 21 on one path and a 21 on another path. It depends on the traffic density that's going to each address block. Configuration, well, you've got your /19 as the first network statement. We've also taken the 19 and split it into two 20s. So the second network statement is one of the /20s. Then you've got your prefix filter, router C out. So A is going to send to C a 19 and one /20. So the prefix list has my 19 and it's got my single /20 as well. Okay. Router B configuration is exactly the same, but with the other /20. So I'm not going to put that one up. Okay. Router C configuration, well again, the upstream ISP doesn't have anything to do. It's like, okay, give the customer the tools, customer can go use the tools, break the network if they want to. It's nothing to do with us. All they do is they set up the peering with the customer, 65534, prefix list customer in. Well, customer's got the /19 address block. He's told me he's going to subdivide it for load balancing, so he's going to subdivide it into 220s. So I'll just set up a prefix filter that will allow the /19 and sub-prefix up to /20 out there. That would be the first cut. Actually, what I find most people are doing is they do a /19 LE, say 24, and that gives the customer scope to subdivide all the way down to /24 if they have to, or if they want to. Okay. Router D configuration is identical to this. There's no difference, and that's a great thing for the upstream ISP. His customer can go and fiddle around with the load balancing that they want, and they don't have to be involved. No support to the customer help desk or to the NOC or anything like that. Okay, the customer's completely in control of their own load balancing. Upstream ISP, of course, has to remove the customer sub-prefix from the external announcements. ISP knows that the customer's got the 19, so they have a filter on router E that only allows the 19 out. Also remove the private AS, but we've seen that already. Just remove private AS configuration option. You could also use BGP communities for this. When I cover communities later on, I think I've got one example that shows how this might work. Right, so the final one of this I want to look at for the break. 2 links to the same ISP, but with multiple dual-homed customers. Now this was written up in RFC 2270. It was Tony Bates and Enka Chen did this when they were at MCI. It was how they handled multi-homing of lots of customers onto the MCI backbone. As I say, it's unusual for an ISP to have just one dual-homed customer. Usually if you have one customer who does this, your sales people think, aha, service, I can sell this, and they go around everywhere trying to sell this service. Okay, point of presence redundancy, connect to the West Coast, East Coast, middle of the country, whatever. It's something they can sell, make more money, and offer some kind of redundancy. Okay, it's a fairly valid, valuable service offering for an ISP. It's better for the ISP than having a customer multi-home with another provider. If your customer multi-homes with another provider, then your customer can compare you with them. And you have to be better than them, otherwise they might change their mind who they pay money to. What you want to try and do, rather than having lots of custom solutions, try and simplify the configuration so that configuration you have works for everybody. So again, try and use configuration templates, peer groups, whatever your favorite router vendor uses. And then each customer ends up having the same configuration. Make it easy for your customer. Prepare a template for them. And when they sign up for this dual home service, or whatever you want to call it, have a dear Mr. Customer, here, use this configuration template. It will work for you. And your customer ends up being very happy because they can go play BGP too. It could be something like this in the picture. Routers C and D are the aggregation routers. Routers A1, B1, A2, B2, A3, B3 for all your different customers. There's no mistake on this slide. You can use the same AS. Okay. 65534, they've just decided we're going to use the same AS number. The reason is, well, AS100 is providing the default route to each of the customer locations. Each instance of AS65534 is announcing their own address block to the upstream. They're getting the default from the upstream. So that if A1 needs to get to A2, he just follows default routing. Okay, so there's no question of routing loops or BGP path protection getting in the way or anything like that. Because all that router C and D are sending to the AS65534 instances is the default route. Okay? Which all makes it easy for you. Okay, we can use the same private AS. RFC 2270 documents that. Well, IPv4 address space can't overlap on the internet anyway, so you've got no problem with that. Customers only hear the default, so there's no issue with the BGP paths. Loop detection. And you get the economies of scale by having the same configuration. In fact, routers A and B configuration are exactly as they were in the previous example. Right? The customer can subdivide the address space and do as they want to load share and so on and so forth. Okay, so it looks the same. So I've got router A1, which basically cut the slide from the previous one and just dropped it in here. Okay, it's exactly the same. So you can give your customer a nice, simple template. Where it gets interesting is for router C. Here we can actually set up, certainly in iOS speak, we can set up a peer group. All our BGP customers are in AS65534. We're going to originate a default route to them, and we're going to filter, have an outbound prefix filter to them that only sends the default. So that's a nice, simple outbound configuration. And then we apply the peer group to all our customers. So customer 1, peer group, BGP customers, prefix list customer 1 in. We want to filter what we hear from our customers. Same with customer 2, prefix list customer 2 in, same peer group. Same for customer 3, prefix list 3 in, same peer group. And then we have the prefix list for the customers. I've just made it in a range of /19 through to /20s. Some people make it 19 through to 24s or whatever the address block is. And you get the economy of scale for your network here. Router D configuration looks exactly the same. You can just pick it up and drop it across your entire network. And it makes it very easy for you. For router E, this is your AS100's upstream connection to other parts of the internet. Again, you strip out the private AS, so you don't get any 65534s floating around the internet. And then you have a filter which only allows your customers out. And notice I've only allowed the /19 address blocks. The customers only get whatever address block they have, so I put that in my outbound filters. You don't have to do it this way, you can do it with communities as well. Communities make this much, much easier. But this is a nice simple example to show you how you get started with this. That's the RFC 2217 style configuration. If the customer's prefixes come from the ISP's address block, don't announce them to the internet. It doesn't provide any extra information. Announce the ISP aggregate only. So here could be, if all the address space came from that aggregate 121.8/13, only announce that. I see instances where ISPs do this type of thing, but you see all the assignments that have been made to the customers being announced as well as the covering aggregate. And there's no extra path information at all. It just gums up the routing table. Okay, so a few of you asked me during the break where the slides were. Well, the slides are, as well as on ftpm.cisco.com, and that location, they're actually also on the NANOG meeting webpage, which I forgot to check before I actually started this. So it's probably easy if you just go to the NANOG meeting webpage and download them from there. But anyway, that's where they are. Yeah, that's right. Right, so where was I? Right, okay, we're going to go look at the two links to different ISPs, but just to finish off the simple multi-homing part. Now, with going to different ISPs, you need to use a public AS number. You can use a private AS number, but you generally find that you've got to agree this private AS number between the two ISPs, and then some people get really uptight about it all, and some people say that, ooh, well, it gives you inconsistent ASs, and that's illegal, and all this other sort of nonsense. I've certainly used private ASs when multi-homing within the UK. We agreed with one other ISP to actually do this, and they were perfectly happy to do it. And it worked fine. It meant we didn't have to apply for or justify a separate AS number for the customer. But in the end, it ended being unwound anyway, and the customer went and got their own AS number and so forth. But you can do it. There's nothing illegal or wrong about doing so. But generally, use a public AS number. They're pretty easy to get hold of, as I said before the break. Address space generally comes from both upstreams. If you get address space from one upstream, you can run into potential problems. Well, again, it depends which part of the world you're in. Here within North America, I don't think it's so much of an issue. For other parts of the world, there's some ISPs who really, really dislike you announcing what they term their address space to other service providers. yet they can't answer the question about how you actually go ahead and multi-home. So, I mean, I suppose it's part of my thing, I always encourage membership of the Regional Internet Registry. So you get your own address block as well as get the AS number that you need. For any service provider, it's generally a better thing to do compared with the price of routers and PCs and other equipment you need for the network. It's not exactly big money. But anyway, what's this inconsistent AS thing? It's basically you view the prefixes being originated by a private AS, and they appear in the internet as being originated from two different ASs. So it looks as though the prefix has been originated by AS200 and AS210. And every now and then, if you're not on the NANOG mailing list, you'll see every year there's usually a question saying, how come this is? Is this something broken? And well, the answer is no, it's not. What's happening is more than often, or more than not, is it's something like this, where a network has multi-homed between two ISPs and they have using a private AS for that multi-homing. You can find out all the inconsistent ASs, so to speak, all the prefixes from inconsistent ASs just by the show iOS command, show IP BGP inconsistent AS. The view that I have, which is from, I've got two views, one in Australia, other one in Japan, and they both show around about 600 prefixes. But obviously, what you're going to see is depending on where you look. So it could be 500, nothing at all, 1,000, a couple of thousand, and so on. So there's quite a few instances of this out there. It's not bad and it's not illegal, but for the purposes of this, we're going to use a public AS, and that's generally what I expect you to use. So the first case we look at is where we have a primary path to one ISP and the backup path to another ISP. So it's primary path only to one service provider, backup only to the other one. As I mentioned before the break, we're going to assume in all these examples that the end AS has a /90 address block. We're going to announce that /90 always. It's the registry's expectation that any allocation you make to any service provider is announced as that, so we're going to carry on like that. So /19 is announced. We announce the /19 on each link. So in theory and in practice, if one link breaks, because we announce the 19 on another link, we get the backup provided that way. And the way we're going to make the backup path act as the backup is to use the AS path prepend. We can't use MEDs, because MED only works if you're comparing paths to the same AS. And if you're connecting to different ISPs, they have different ASs, so you can't use the MED. ISP1 cannot see what MED you've sent to ISP2. There's no way of doing that. So we use the AS path prepend. If you remember from the BGP path selection process, the longer the AS path, the less preferred. So the shortest AS path wins. So if you use an AS path prepend, it makes that path look longer if you view it from the internet. Therefore, that's preferred. Therefore, it's your backup. Okay, so pictures like that. A to C is the primary path, B to D is the backup. From A to C, we announce the /19 block. From B to D, we announce the /19 also, but with a longer AS path. Inbound, we're just going to accept the default route. Because again, we're saying, we're sitting at the edge of the internet, so nearest exit will be fine for most cases. So, router A configuration, this is the primary path. We just send our /19 out, so we see a /19 there. Prefix list aggregate out, send aggregate out, default in. There's nothing amazing there at all. It's exactly what we've seen before. Router B, well, router B, it's similar to what we've seen before, but with one difference. No MED, we're now going to use AS path prepend. Okay, so we've got prefix list aggregate out, as before, default in, as before. Router B out, route map, so there we set our outbound policy. And the router D out, this says we set the AS path prepend to 3 more instances of AS130. So if we sit out in the internet, if we look through the path that's come from router A, we should see AS130 and what's that stream, 100. Here's the AS path. If we look around the other direction, we should see 4 instances of 130 and then AS120. We do the path selection, well, the one going through 100 is shorter, and that becomes a preferred path. So we've made this nice and long. 3 is enough. The average depth of the internet is 5 ASs. I mean, there's still people out there who like doing 20, 30, 40, 50 times pre-pan. The longer the pre-pan doesn't make it less preferred. Okay? The typical depth, the biggest depth of the internet that I've seen with unique ASs has been about 22. Okay, and that's quite unusual. Generally, it's about 5, 6, 7, 8, 9, 10. That tends to be the typical depth. So you do an AS path pre-panned to the sort of depth that you actually need. If we get time to do the case study, I'll show you what I did. And then router D in, well, what we're doing here is the default route that we're hearing from router D, we're just setting a local preference 80 to make it the backup path. So that's what we did before going to the same ISP. And again, this one will work just nicely. We AS path pre-panned for outbound routing announcements, inbound routing announcements, we set a local preference low for the default route. As before, this isn't really a very common situation. People don't like having circuits lying around with traffic on them. So we look at the load sharing example. And this is the one that, well, I suppose potentially, if not done properly, can cause, I wouldn't say problems, but it causes stress for the internet routing table. We've got our aggregate of /19 address block. We announce that. We always announce the aggregate. I was talking about net police concept before, and ISPs filtering and the registry allocation boundaries. If you announce your aggregate, you have no issue with any of the allocation boundaries. So what we do here is what we did before. We take our 19, announce it out both paths. We also take the 19 and chop it into 2 pieces. We don't do, ooh, this is 32 Class Cs, I'm going to announce 32 Class Cs. We don't do that. Class Cs disappeared in 94. Starts something nice and simple. Take the 19, chop it into 2. Send 120 out one path, the other 20 out the other path. All the traffic for this 20 comes in this way. All the traffic for this 20 comes in that way. So you've got a very, very basic inbound load sharing. Okay. So the picture really represents what we're going to try and do. By announcing the /19 block out of each link to ensure that if one link breaks or one path breaks, we get back up through that way. And even if there are ISPs on the internet somewhere that are filtering out the /20 because it falls under some magical limit that they've set for what they're going to accept, you still get connectivity because you're announcing the /19. So your network will be able to access their backbone. Looking at the configurations, we've got the /19, the /20, the prefix list for the first block, so we announce the /20 and the 19 out on this path. Router B configuration is very similar. We've got the /19, the second /20, the outbound filter called second block, and down there the second /20 is outbound. And that achieves the configuration for router A and B. And that will do your very, very rudimentary load sharing of inbound traffic. It's just very basic, but it shows the first steps, and that's an important thing. It's the first steps where you start. Okay. I always try and encourage people to pick up this sort of example. Start here, then make it more complicated. Don't download something you managed to find on Google from some tier 1 ISP who's got 30 pages of BGP configuration and modified it to suit your situation. That doesn't work so well. They've got this really specialized one for a very good reason. Try and take something that's really simple, like this, and work from there. I mean, I do a lot of workshops for multi-homing and so forth, and we start with these simple concepts and show people how to make it, build it up based on these concepts, and they can pick these, modifying the prefix list a lot easier than presenting with something highly complex. More controlled load sharing. Well, here's an idea of where to go if you need a little bit more control. First link, you announce your /19 as normal. Second link, you announce your /19 also. But we announce it with a longer AS path, and we also announce one sub-20 prefix. This one pollutes the internet routing table slightly less. Here you announce it just a 19 and a 20. but you're announcing one of the 19s with a longer AS path prepend. And there you can vary the sub-prefix size and AS path length prepend until you get perfect load sharing. So this is another way you can engineer how your load sharing functions. Okay, so A to C, we're just the standard configuration of announcing a /19 out. Again, in both cases, we accept the default route in. For B to D, we send a 19 out with a longer AS path prepend, or AS path prepend, and we announce the /20. So what happens? All the traffic for the /20 will come in through AS 120 to 130. All the traffic for the other /20, well, that will probably load share. Some of it might come through AS 100. Other parts of it might come in through AS 120. It just depends on the paths to the rest of the internet. And that's what I mean by more control. You definitely know that traffic for single /20 is going to come one way. For example, that /20 might be your dial address space. And so you know that your dial users are going to try and use every single bit of bandwidth they can get. Whereas the other /20 might be commercial or something like that. And so you want to give them more bandwidth when you can and take bandwidth away when it's not there. So that gives you a little bit more control. You can vary this sub-prefix size also. That could help the situation. Maybe make it a 21 or a 22 and so on and so forth. You can vary all these things without announcing a huge slew of address space or sub-addresses to the internet. Router A configuration is exactly as we've seen before. We accept the default in, we send the aggregate out, nothing special there at all. Router B, we generate the prefix for our /19 and 1/20. Inbound, we accept the default. Outbound, we send the sub-blocks. So we send, the way I've made it, I've made /19 and NA/20 as well. I allow out, just an example how to do it. The route map, outbound, there we set a policy. That's how we do our AS path prepend. If the prefix being sent matches the aggregate, we're going to do a 2 times prepend. We could do a 1-time prepend, 3-time prepend, 4-time prepend. It depends on the topology of the internet. Connecting between, say, your upstream ISPs and, well, I suppose the center of the internet. If I jump ahead a little bit, given I've not much time left. If you go to some of the looking glasses, generally a lot of the service providers will look at many of the US looking glasses. That tends to be more the center of the internet than anywhere else, where most of the content seems to be lying around, and measure it from some of the US looking glasses back to the home network. You can get a pretty good idea of what AS path prepend you need to do to make one path primary and the other one backup. So that's quite handy. So this is more commonplace. This is the sort of thing that people try and do, subdividing bits of address space, sending leaks out, and even if they're filtered somewhere further along the internet, you've managed to achieve the local load sharing that you want to do. So we've subdivided address space frugally here. We haven't taken our 19, chopped it into 24s, and just spew them out. We're doing it carefully. So let's move on to the next bit. Service provider multi-homing, or subtitle I've called it BGP traffic engineering. The previous example really only dealt with load sharing of inbound traffic. So this is what ISPs at the edge of the internet cared about. But if you're not really at the edge of the internet, or maybe you're a content provider and you've got more outbound traffic than you have inbound traffic, what do you do about that? Because maybe nearest exit is not good enough. So transit ISPs, as I was saying, they strive to balance traffic flows in both directions. You want to try and balance link utilization, try and give symmetric traffic flows. Even though internet is quite happy with asymmetric flows, it tends to be nicer for customers if traffic goes between here and there, rather than going there and then all the way around the world to come back and through another path. You want to try and keep the latency as low as possible. And I've called this the original traffic engineering. I've found that if I mention traffic engineering in the last few years, people immediately think of MPLS. But actually, traffic engineering was around a lot longer. We all used it for BGP. That was the original traffic engineering, by playing with the BGP policy to try and massage the traffic flows to go in the ways you actually wanted them. Now, balancing outbound traffic requires inbound routing information. you can't really balance outbound traffic without inbound routing information. And the standard solution is, you need the full routing table. If anybody who wants to multi-home, the first email is sent to the upstream ISP is saying, I want to multi-home for blah, 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 whatever reason. And the upstream says, well, to do this, we need to give you a full routing table and we'll charge you, $2,000 a year for that, and you need to take this router, and we can sell you this router if you want, and you need this bandwidth of circuit because you can't fit a full routing table on anything less than an OC12 and so forth. All these kind of things which are really, I don't know, they must be on some checklist somewhere that people don't really think before they actually spout it out. But it's really necessary. Some places where you can't afford any of these things don't have access to any of these things. It's just a complete routing mallet. You don't need this huge amount of information. The full routing table is like, you don't need the world's telephone book just to find out the phone number of people who live in your street. It's useless information. As I say in the last point there, it's much easier just to keep it simpler. And it's a lot cheaper as well. You don't need to go buy massive routers or upgrade big circuits or do anything else like that. You don't need to carry n copies of the full routing table to multi-home. There's some common myths. Things like you need the full routing table to multi-home. People who sell router memory would be quite happy for you to believe this. It's probably only true if you're a transit provider. If you're providing the full routing table to other people who need it for various reasons, you're more to the center of the internet, you kind of need it because life gets too hard trying to do load balancing without it. Second myth, you need a big router to multi-home. Big routers tend to be related to data rates, throughput, rather than actually carrying routing tables. I've done multi-homing on routers about this size. All you need is two interfaces. Must be able to use BGP, talk BGP to two peers. Must be able to handle BGP attributes. And must be able to handle at least one prefix. It's not exactly an amazing task. And I say I've done it on little routers that have the BGP configuration. And they work just fine. People have been multi-homing with those more than happy. And also, with my developing countries hat on as well, I'm faced with several providers in many developing parts of the internet who just say, oh, well, I want to multi-home, but my upstream ISP in Europe has said I need this router. And this router is more than our income for the last 10 years. I'm not quite sure what I'm going to do. And it's like, well, just use what you've got. Don't mind what they say. So I usually get involved, I get an account, email account with them, I speak to their upstream. They don't know it's me, they think it's just somebody local. And I say, yeah, we'll take the full routing table and make up model numbers and so forth. And then they're all quite happy. They send us a full routing table, we throw it all away and just keep the bits that we need. And that works. And so there are people running 5-10-year-old routers that, well, probably most of us see in museums now, and they work perfectly well. No problems at all. Third myth, BGP is complex. Well, all the BGP gurus would like everybody else to think BGP is complex. In the wrong hands, yes, BGP can be very complex, but actually, if you keep it simple, think simple, BGP is actually pretty easy. Now, some of the strategies, before we sort of jump into some of the examples. You want to try and take the prefixes you need to aid your traffic engineering. Okay, so the traffic engineer you're going to look at is connections between you and your neighboring ASs. So we're sitting here in the US. Who cares about prefixes in India, Russia, what else? China. Who cares about those prefixes? They're not going to help your load sharing sitting right here. You're trying to load share between two ISPs sitting locally a few miles away. Who cares about all those prefixes somewhere else in the world? As long as you know you can get to them somewhere, that's all that really should matter. So why jumble up all your routing just with those? And one thing that I find, well, I've always found has been really useful is to use a NetFlow. NetFlow's been around something on Cisco boxes for 8-9 years. And that's a very, very useful way of finding out where all your customers are going, what the important sites are to them, and then trying to figure out which path you want to take to get to those sites. Okay, other router implementations all have similar type of flow data as well. So that's a really, really valuable way of trying to find out where your customers are going to. Prefixes originated by your immediate neighbors, and their neighbors will do more to aid load balancing. That's generally very clear. It certainly helps with keeping traffic symmetric. And use default routing as much as possible. If you're going to use the full routing table, you probably only ever need one copy of it. And then you can rely on defaults and local prefixes for everything else. So all these examples I'm going to show you will work on that principle. So we should have time to go through these 6, I hope. So the first one's a nice easy one upstream, one local peer. Actually, rather than reading them out, I'll just work through them. We need BGP for all these, of course. We need a public AS number. All these examples assume that the local network has their own /19 address book, just to keep it easy. So this is a very common situation in many regions of the internet. Generally, you have an ISP. They connect to their upstream somewhere else, and life is good. Then they discover that traffic that goes from them to the neighboring ISP goes to their upstream. Upstream is charging money for all this traffic, and you think, I could save money just by running a circuit to a local guy. Okay, so you've ended up multi-homing. So traffic between your 2 networks stays local, and traffic that has to go somewhere else goes through the upstream. So you save money. And probably here in North America it matters less, but certainly for some parts of the world where you're looking at jumping across countries for some of this, starts costing lots of money. So, simple picture like that, your AS110, 120 is your local peer, 130 is your upstream. So, some of the rules, or some of what we're actually going to do, we announce the /19 aggregate that we have on each link. We always announce the /19. It's like every example here, we're always announcing the 19. We never announce less than that. We accept the default route only from the upstream. The upstream is how to get to the whole internet. So default route means the whole internet. So we use network 0 or a network which can be used as a default. And we accept all routes originated by the local peer. So if the local peer has got lots of local prefixes, we just get them to send them to us. And then all the traffic that has to go to a local peer has specific paths, and it goes over local peering. Anything else goes through the upstream connection. So the route to A configuration, this was our local peer. We've got a network statement for our address block. Prefix list, my block out, so that's my /19 I'm sending outbound. Prefix list, AS120 peer in. Those are the prefixes from my peer in AS120, and he's sending me a /19 and a /20. So that's an example. So that's maybe how you configure that. If AS120 wants to send you another prefix, you're going to have to go in here, add it to the prefix list, and you keep it tightly under control. Never assume that your neighbor is going to do his own filtering properly. And I'm sure some of you have met as many cases as me where people have assumed that the peer is going to do the peering, and then one day you wake up with all sorts of garbage in your routing table. So always filter what your peer is going to send. Okay? Ask them what they're going to send. If they're going to send something more, get them to send email saying what the extra prefixes are going to be. An alternative configuration, I mean, if you know your neighbor very well and you can go down to the bar and have some beers every weekend or week or whatever, and you trust what he does and he's as truthful as you are, then maybe you can use an AS path filter. So I've picked up the same thing here. This says anything originated by AS120, I'm going to allow it. This is fine. I'm generally happy with this with people who better know what they're doing, especially if they can trust their neighbors. In fact, what you find that most ISPs do is they take a combination of this one, where they filter the prefixes as well as the AS path filter. And their argument is, oh well, you know, we always talk about redundancy. So if I break one filtering mechanism, at least I have the other filtering mechanism as a backup. So we have the filter list as well as the prefix list. So we filter on the AS path as well as the prefixes. So that can be the double protection there. Router C configuration, this is to our upstream. This is the same as we've seen before. We accept the default route in from upstream, and outbound we send just our /19. Okay, so that's fairly standard. Okay, as I said, 2 configurations are possible for router A. Some ISPs actually do both, and I've got a general preference to do both as well. Just from past experience, once you've been stung by just having a single point of failure, you tend to put in a second protection just in case things go wrong. Now, the next one that's actually pretty popular in many parts of the world is getting one upstream and then you join an exchange point. In fact, what happens is the many ISPs in a region, they all have upstreams. Okay, there may be a city being served by half a dozen ISPs, but they all connect to upstream provider. And the upstream provider, of course, is charging them traffic charges, and they're thinking about this traffic's all just staying within the city, yet we're paying this upstream ISP for sending local traffic. So they all get together one day and decide that this isn't very good. We're all spending their money on somebody else. So if they form a local exchange point, then they can all peer with each other for free and only send into the rest of the traffic to the upstream provider. So a picture could be something like this. So again, router A connects to the exchange point in this case. It peers with the other service providers at this exchange point. Router C goes to the upstream. So as we've done before, we announced the /19 aggregate everywhere. It's to every neighboring AS, so both to the upstream and to every peer at the exchange point. We accept the default route only from the upstream. We don't need the full routing table from them because it doesn't give us any extra information. And we accept all the routes that are originated by the exchange point peers. Okay, so everything that they at the exchange point will send to us, we accept. Okay. Looking at the router A configuration, well, we've connected to an Ethernet. I've put in the reverse path forwarding check there. That's generally pretty good practice, certainly at an exchange. If you don't peer with every ISP at the exchange point, it stops people who you don't peer with from sending the traffic. And then for the BGP configuration, again, we can use the economies of scale of things like peer groups. So we can set up a peer group with the filters and stripping the private ASs, which is quite handy to keep things easy, and then apply this to each exchange point peer neighbor. Of course, we still filter what each one sends us. Okay? You don't just accept any old thing. I've been to some exchanges where they accept any old thing and announce any old thing, and end up with exchange point members re-announcing prefixes from other members back to the exchange, which is generally not very good news. And then there's just a list of filters. Note one thing though, the router A does not generate the aggregate for AS110. Now the reason I'm saying this is generally because people who participate in exchanges, this is getting a little bit away from multi-homing, but it's a good practice thing. I'm not quite sure where there's any of this should really fit in. Exchanges tend to be well away from where the main ISP operations are. So what ISPs tend to do, because ISPs aren't really critical infrastructure. Exchanges aren't critical. They're handy for sending huge volumes of traffic at very low expense. Okay, so what people tend to do is put a router at the exchange and then run a single circuit back to the backbone. If you generate the aggregate on the router that's at the exchange point, well, sure, it'll work fine. You'll announce this aggregate to all the other peers. If the circuit between the router and the exchange and your backbone breaks, well, your router at the exchange will quite happily announce your aggregate. Whereas you'll try and back up through your external connections, traffic will go out, try and reach the exchange point peers. They see the best path to your exchange point router. Your exchange point router goes, I don't know where any of this has to go, null zero, boom. So you basically black hole yourself from all the local peers. So it's quite important not to generate the aggregate at the exchange. Again, I've been burnt by this many, many years ago. I've met many people who've been burnt by this as well. So generating network aggregates in the core of the network is actually pretty important. And the BGP failover works as expected. So router C that goes to the upstream, that's the same as before. We accept the default inbound, we send our /19 aggregate outbound. Okay, so router A configuration, prefix list is high maintenance, but it's generally safer to do. We find that many IXs have mailing lists, some IXs use routing registries. So between the two, you can keep the prefix filters up to date so that everybody at the exchange knows what they expect to hear from the other providers. I've got reverse path forwarding check on the IX facing interface, and I don't generate the aggregate of my AS at the exchange point router. And that all works quite nicely. And again, that configuration, well, it's the last exchange I was involved in, set something like this was in Nepal. I mean, we actually had to do the whole works that I described before the break. That was convert all ISPs from using static routes, or 2 ISPs from using OSPF. So convert them all to running OSPF and IBGP as I described. Then getting eBGP to actually work across the exchange point and get them all to do it properly. And that exercise is actually, I think I spent about 3-4 hours with each service provider, and that was all that was necessary to convert all these networks over, plus to work at the exchange. And it all works beautifully simple. Local traffic stays local, international traffic all goes over the external connections. So just some configuration recommendations. And again, not quite sure where to throw these in, but here's as good a place as any. For private peers, the peering ISPs should exchange prefixes they originate. Okay? Sometimes they exchange prefixes in neighboring ASNs too, but that's all part of the commercial agreement between the private peers. So be aware that the private peer eBGP router should only carry the prefixes you want the private peer to receive. Some people put the full routing table on their private peering router, but get worried or puzzled why there's so much outbound traffic. And it may not be an issue here in North America, or maybe it has, but nobody's really mentioned it. But it's certainly a big issue in many places that I go, where people are trying to stop stealing of bandwidth. And there may be private peering arrangements and people who have been provided a private peering service, too many peers, provided a private peering service, they point a static default route to their private peer, and they send outbound traffic over to their private peer's network, because the other ones carry the full routing table. So you kind of got to watch that. Otherwise, unintentionally transit your backbone, I think is my polite way of putting it. At the exchange point, well, it's a similar thing here. The peering ISPs at the exchange will only exchange prefixes they originate. Sometimes they exchange prefixes from neighboring ASNs too, it just depends on the deal. Second big thing, be aware that the exchange point border router should carry only the prefixes you want the exchange point peers to receive and the destinations you want them to be able to reach. So don't put full routing tables on there unless you want them to use you as outbound transit. Okay, it was funny at the last APNIC meeting, that was exactly the issue that one of the exchange points brought up, how to try and guard against this. And they were a bit surprised because they didn't think this was possible. And I was like, well, actually, yes. It depends how you configure your BGP. Okay. And the final point, if the IXP router is at the exchange and it's distant from your backbone, don't originate your address block there. I've been burnt by all these in the last 2 slides, so that's why I'm putting heads up here. Just if you're participating in anything like this, you do well to check the configuration of your routers. Okay, 2 upstreams, 1 local peer. You've got 1 upstream, you've got 1 local peer. You're not wildly happy with your first upstream, or maybe you want better paths, or somebody's offering you a better deal, or whatever. So you want to connect to the second one. What do? Well, it's just a case of taking the same thing as we did before. We announce the /19 aggregate in each link. We accept the default route only from upstreams, from both of them, and accept all routes from the local peer. So router A configuration, that's a local peer, is exactly the same as before. I mean, there's nothing different there. We send the /19 aggregate to them. We accept all the prefixes they originate. We use the prefix filter to filter the prefixes and or the AS path filter to filter their AS. Now, router C, we accept the default, we send our aggregate out, that's fine. Router D, we do the same thing. We accept the default in, we send our aggregate out. But this is not exactly wonderful for outbound load sharing, because all it's going to do is take nearest exit, if you're lucky. So you might, if you're lucky, you might get some kind of load balancing, but more likely you're just going to get all your outbound traffic going on 1 service provider, which is not too useful. And you've got 2 service providers to try and load balance between the 2 circuits. Okay, so that's a simple configuration. You can do it on very inexpensive routers because they're only carrying about 3 or 4 prefixes, but unfortunately it's not very practical. Now, the better configuration options, and some people go, oh, this is difficult. Okay, I'm going to take full routing table from both providers. And it's like, okay, why do you need 300,000 prefixes to try and decide load balance between two circuits. It sounds a little bit like overkill. So what to do is take the default route from one upstream and then take some routes from another one. That's the same thing. Okay, let's have a look at it. Let's say we're going to take full routes. Okay, so we set up our BGP configuration with some router C. We've got our inbound filter there. Full routing table doesn't mean we accept all chunk. Full routing table means we accept all legitimate prefixes. So we throw away RFC 1918 and friends. Unfortunately, the projector's chopping off the right-hand side of the screen. That says RFC 1918, so private address space and friends. I mean, for RFC 1918 and friends, you best go to Rob Thomas's Project Gimlet website and go to the Bogon list there. That's pretty much what people use. Outbound, well, just your /19 address block. Yeah, there's the URL for the Project Gimlet website. Just pick up the prefix filter that's used there. If you're going to do this, keep it current. So when Rob sends an email saying, update, I put a new version up, you meant to actually go there, download it, apply it, not fall asleep and never do it. Then you start chopping off some of the newer parts of the internet. What else have I got here? Okay, route map AS130 load share in. Okay, that's a mysterious route map that's going to do some kind of load sharing. And what it's actually going to do is it's going to match all the prefixes that have an AS path that looks like this. Now, hopefully you all know your AS path, well, regular expression language. Basically means if you hear any prefixes originated by AS130 or any instances of AS130 prepend, or any prefixes from AS130 and their immediate neighbors, we're then going to set local preference 120. Okay, so you see what this is doing. If we go back to the picture. There's the picture. Okay, there's the picture. What it says is we're going to accept full prefixes from AS130 and AS130's neighbors. That means if any traffic is going to 130 and its neighbors, it'll go out through router C. That's why I'm setting the local preference to 120 there. Okay? It kind of makes sense to do that. You say AS130 is in Europe and AS140 is in Asia, and you're sitting here in North America. Right. Okay. Why would I want traffic that's going to go to Europe to go out through my Asia connection? It means that it ends up going all the way around the world. That's an extreme example, but that's the sort of thing I'm trying to get at. You want to try and keep traffic symmetric and going in roughly the right direction. So if I take the prefixes from 130 and their neighbors, then outbound traffic to 130 and the neighbors goes through router C. The return traffic, because they'll see the best path directly through 130, will come straight back. So you get roughly symmetric traffic going in that direction. Okay, where am I? And for everything else you hear from AS130, we're going to make it a low local preference, so we set it to 80. Default is 100 in this case, which means that every other destination will go through router D. Router D configuration is easy. It's just accept the accept the full routing table, allow everything in apart from RFC 1918 and friends, as I said before. Okay, so that's the full routing table one. I think I've just described most of that slide, so I'll just jump on. It's expensive, need lots of memory, needs more CPU to try and handle it. You need to play preference games. The routing table, when I looked at it, well, yesterday, 149,000 prefixes in my view. So that's almost 300,000 prefixes you'll be carrying in your routers, which is quite a lot. You'll need to play preference games, as I said. You'll need to do some fine-tuning. The example I showed you is where you would start, but then you need to do fine-tuning after that, of course. Of course, it doesn't consider any inbound traffic, but we know how to do that more or less. Okay, so that's a full routing table version. 300,000 prefixes on a router, 256 megabytes of memory. Send your checks to whoever for more memory. Partial routes is actually much easier to do. That means you don't have to upgrade routers also. You ask one upstream for a default route. Default route is pretty much the same as saying, I know how to get to the whole internet. By the way, before you ask your upstream for the default route, make sure that they have redundant connections to the internet. it's a bit silly to get a default route from your upstream if they've only got one connection to the internet as well. Because if that breaks, then you get black hole. So I've seen some people who've followed this presentation to the letter, but they forgot to check that their upstream is actually multi-performance. So that's kind of important. So it's easy to originate default towards a BGP neighbor, simple configuration. Ask the other upstream for a full routing table. It's very difficult to go to an upstream and say, can you put this AS path filter, prefix filter on your BGP session with me? And they'll just laugh at you. Or they'll maybe send you an account for, I don't know, a few $1,000s to do it because it will put unnecessary stress on their routers or something. So just don't do that. Just stick with what they can do. They can either send a default, which is nothing at all to you, or they can send you the full routing table. I haven't found many ISPs who are happy to customize their announcements towards you. Some do it, but the bigger ones tend not to want to do this because it's a support burden. So ask them for a full routing table. Then filter this routing table based on the neighboring AS number in exactly the same way that we kind of did before. So rather than doing the local preference that we did before, filter it. So we accept prefixes from, say, AS130 and AS130's neighbors, and discard everything else. So all you're carrying on your network now are AS130 prefixes, AS130's neighbors prefixes, a default route from AS130, a default route from whatever the other one was, AS140 I think, and all the prefixes from your local peer. Okay? Most of what your upstream will send you in the full routing table is thrown away. There's no harm in doing that. So what do you want to do for here? Well, again, you want to put your prefix filter in for accepting everything. So it's RFC 1918 and friends again. You want to accept the default route though, because if you're going to do a default originate plus a full routing table, you need that. Filter list 10, that is the AS path filter. So even though this will accept all prefixes apart from the bogons, the filter list will do the AS path filtering stuff to only let your neighboring AS and their neighbors into your network. And then we've got a route map tagged default low. Because we want router D to be the default, and we're using the default route from AS130 as well on router C here, we need to make this default route a lower priority than the default route on router D. So you see what's happening? Default route is through router D. If router D breaks or the upstream breaks, then we get back up through router C by the default route that's been sent in here. Traffic that goes to AS130 and its neighbors goes out to router C. Traffic to everywhere else on the internet goes out through router D. And the rest of the configuration, okay, there's the AS path filter for allowing 130 and 130's neighbors in. So rather than being a local preference, a filter being used for local preference setting, as we did in the full routing table example, it's used for actually filtering prefixes. And then the route map there, if the prefix being sent in as default route, we set local preference to 80, otherwise we just leave everything else alone. Okay. Router D configuration, very, very simple. Okay. Accept the default in, send your aggregate out as before. So that's a very straightforward configuration. And what's amazing is if you configure this, it has exactly the same effect as the other one did, kind of full routing table. So here you get away with maybe a dozen or so or a few hundred prefixes. The other one, we were trying to do the same with almost 300,000 prefixes. And the big advantage with this one is, well, you're not chewing up a huge amount of router CPU processing all these BGP updates. You don't need a huge amount of memory. It's much, much easier to configure, it's much easier to handle. Okay, you don't need to worry about your iBGP in the network because you're carrying the minimal number of prefixes. Okay? Let's say I know many ISPs have actually taken this and they've converted the full routing table solutions into something like that, and they've not noticed any loss of connectivity or performance or anything else, even though they had people of doom coming along and say, oh, well, you can't do it like that, it's not going to work so well, and you need to carry the full routing table, otherwise you won't get to the whole internet. It's like, well, hang about, the default route is saying the same thing, so it all works just fine. Not expensive, you need to do a little bit of AS path filtering, you don't need to play any of the local preference, games, and all the rest throughout your network. And it works quite like this. This is quite a good first step. And I'm not saying that you just pick this up and drop it into your network, it's going to work. You will need to make modifications. There may be some neighboring ASs you don't want to receive prefixes from. For example, if your upstream connects to, who's it, say, MCI or was it AT&T, they're the two biggest contributors to the routing table at the moment. Do you really want all these prefixes coming in? So there may be modifications you have to make there. But as a first step, it's pretty good. In any cases, I've used and worked with people who have started like this and modified it to suit what they actually need. When the upstreams can't or won't announce a default route, then just get them to just use one other prefix that they send you as a default. Or you can try and do it via IGP, get the IGP to inject the default route into your network. So something like this. Default information originate OSPF, that will set a default route into OSPF as long as a default route exists somewhere else. So if you have a static default route pointing to this particular upstream, if the link to the upstream goes down, OSPF withdraws the default route. So that's quite a handy feature. And you don't have to rely on the upstream ISP sending the default. Okay, there's nothing more there. No, otherwise the configuration is exactly the same. Okay, so if the serial interface goes down, that static route gets removed. OSPF doesn't see the static route in the routing table, so it removes the static route from the OSPF link state database. Router D, that's the primary path. Again, we don't get a default route from this upstream. So metric 10 is higher priority than metric 30, so this becomes the default path out. Inbound from the upstream AS1 party, get no prefixes at all because he won't send us a default route, he'll only send us the full routing table. So we say, well, stuff you, throw everything away, and we just generate our own default. Again, when the link to the upstream goes down, then we fail over, and OSPF removes the default, and we see the default coming from router C. So that's all that. That's all that I've said. Okay, now a super complicated one. It's a complex example which tries to bring everything that we've done so far together. So connecting to two transit upstream providers, two regional providers, private peers for peering purposes, connecting to a local exchange point as well. It's a little bit extreme, but there are quite a few ISPs who fall into this particular boat as well. So what they really want to try and do is go to the exchange point, so participate in exchange points that local traffic will stay local. You maybe have local private peering connections with some ISPs who don't want to go to the exchange point or maybe don't want to use it or so forth. You've got regional transit providers that may provide transit for several states or region or several economies. And then you've got your upstreams, which may be, for example, the tier 1 providers in the internet. So the two upstreams, in this case, will provide you with transit, full transit to the whole internet. Your regional upstreams may also provide you with transit to the internet, but it'll be one hop longer than going directly to some of the tier 1s. So that's just a hand-waving sort of example. So as before, we always announce the /90 on the link. We accept the partial or default routes from upstreams. So one upstream we can accept the default route from, other one we probably can accept the full routing table and throw most of it away. We accept all routes from a local peer because it's just a local peering. So everything they originate, we accept. Everything we originate, we send to them. From the regional upstreams, we accept a partial routing table from them. See by a minute. An exchange point, of course, we accept everything that they originate. So router A, that's a local private peer. We accept all the local routes, keep local traffic local. Its example, a few steps back, we had the local peering configuration. Just exchange local prefixes. Router F at the exchange point, same deal as in the previous, in the earlier exchange point example. Don't originate or aggregate at that router. Don't carry the full routing table on that router. Don't have a default route on that router. Now, the regional upstreams, here can get a little bit interesting. The regional upstreams, the reason we connect to those is to save transiting our tier 1 upstreams to get to service providers who are close to us, but we don't peer with locally. Now, probably in North America that makes less sense, I don't know, but certainly parts of Asia and Europe this makes quite a lot of sense, where your upstream may well be a US-based service provider, whereas your regional could well be a regional provider within the continent. Why go across a huge block of water when you want the traffic to stay local? So from these regional upstreams, you probably accept what they originate and what their customers within that region originate. Because it makes sense, because that way you keep traffic off the undersea cables, or worst case, off the satellites. Because this kind of makes sense. So what you do there, you can ask them to send the default route, as well as sending the full routing table. You could try asking them to send just their prefixes and the customer prefixes. Some may have the tools to do that, but if they don't, then you can apply the AS path filter yourself like that. They're also going to provide backup to the internet. That's why we accept the default from them. It's going to be less preferred path than going direct, but at least they provide you some backup in the case that your own connections break. And router E is the same thing. We accept the default from them. We've made this default slightly more important than the other one, rather than having them the same. So at least there's a well-chosen cascading failover as upstream links break. So if the two upstreams break, this becomes preferred path for outbound traffic. And if this one breaks, then the other one becomes preferred path for outbound traffic. Router C, we call it the first tier 1, we accept all the customer and AS neighbor routes, so we do the same sort of AS path filter as we saw in the earlier example. Ask them to send a default, full routing table, whatever, or something you can use as a default. Make this default, go to the next highest priority, make it 80 for example. This will provide backup to the rest of the internet if the link to the second tier 1 goes down. And this is the primary outbound path. If you've got no more specific information, all your traffic will go out through this ISP. So this is the starting point of trying to set all this multi-homing up. The picture, when you first look at it, it's quite intimidating. You've got all this to do. It's like, where do I start? But if you work through it methodically, if you try and itemize what each neighbor is going to do for you, you know when you're going to get to the exchange point, you know what the local peers are like. So that's easy. Regional upstream, well, what makes sense to get from there? Well, everything that they connect to closely. Because you pay them X amount of money, and it's probably a different amount of money compared with going with upstreams. So it's probably cheaper to access these regional and their customers than it is to go up through your upstream providers. And then as a last resort, you go to upstream ISPs. And if you think through how to do all this, you can probably get away with this with only maybe one version of the full routing table. Or you can even get away with a lot less. I've only seen one ISP who's actually done this without using full routing table in many instances. And it works perfectly well for them also. So let's go back to so that's the summary. To modify the load sharing, you just have to tweak what you hear from the two regionals. You just have to play with the AS path prepends. You maybe find there's some ASs in the AS path you want to throw away. So the case study, which I may not have time to do, has some examples of that, where the particular prefixes from particular ASs you don't want to hear, so you just discard those and accept the others. But this is a starting point. You start from here and then try and work through to modify your load sharing. What about the outbound announcement strategy, which try and determine incoming traffic flows? Always keep announcing the /99 bit, certainly over paths that are intended to provide backup. So to the two regionals and the two upstreams, announce your aggregate. To the local peers, you need to do that as well. To the exchange point, you need to do that also, otherwise they won't be able to send traffic to you. You can send /20 and 21 more specifics if you want to, or 22s, or 23s, or 24s, but do it frugally. Okay. Try splitting the 19 into two pieces and see what happens. If that's not enough, split one of the 20s into two 21s. see what happens. If that's not enough, split the other 20 to two 21s. Okay? If that sounds a bit too random, take a look at the net flow data and see where the busy, or the hot spots in your address space are. See the busy parts of your address space. If it's dial pools, well, you can renumber dial pools. Customers don't really care what IP address they have because they're all dynamic. So if it's the dial pools are concentrated in one part of your address block and it's overheating, set aside another address block and split the pool between the two. And then at least you can load balance over the external circuits that way. That all works very well. Unequal circuit capacity, similar ideas. Use the AS path filters, think about how you do the addressing and so forth. The upstream will only give you full routing table or nothing at all. Again, AS path filter, prefix filters are very useful. The OSPF or ISI's originating default route works very well too. Now, just some examples. This is what I've called the multi-exit backbone. It was a situation I was faced with a few months back. Well, I think the people just looked at it, looked at the picture and went, help, can't do this. We've got many different exits to different service providers. It could be a large regional ISP with a variety of international links to different continental locations. And load balancing here can be a bit painful to set up. But what they were doing was quite literally taking the address block and chopping it up into 24s and announcing a 24 here and a 24 there, and just generally trying to do things without any strategy whatsoever. The whole addressing plan and everything was just, it was all over the place. There's no real strategy of trying to make the multi-homing work right. So I've actually kept the bandwidths as they were, just so you get a flavor of what they were trying to do here. They had three major locations. A, C, and D were the major locations. A and B are close together, but I'll separate them out for this example. So A had two uplinks, an OC3 and a T3. C had two OC3s and a T3, and D had an OC3 and a T3. And they were like, we have no idea how to load balance handle this. The exchange point, of course, is easy. That's local traffic, so doing the BGP for that is very, very simple. We just accept what we're going to hear from our neighbors at the exchange point. And well, my first answer to them was, well, you need to be methodical and use some fairly logical steps. And just sit down with a big piece of paper and write out what you're trying to achieve. And first, do the easy one first. The exchange point, that's easy. It's usually non-transit. Most people who go to exchanges want to be non-transit because they don't particularly want their bandwidth to be abused. So it's preferred path for all the prefixes learned this way. So that's nice and simple. For the outbound announcement, we just send our address block or the address blocks we have. Inbound announcement, we accept everything originated by the exchange point peers. Step 2, where does most of the inbound traffic come from? Well, we go to that source location and check looking glass trace and the AS paths back to the neighboring ASNs. i.e. which of AS120 through AS170 is the closest to the source. Okay, so we go back and remind you what all the pictures are. So 120, 130, 140, 150, 160, 170. So we're connected to 6 different upstreams. So try and figure out which one's the closest. And then we apply AS path pre-plans such that the path through AS140, AS140 has the dual OC3 connection. We make sure that that one is one AS hop closer than all the other ASNs. Okay, so that's for incoming traffic. So we just do pre-plans on all the outbound announcements at the other place. And what these guys were actually doing was going, oh my gosh, and they've got, I think it's /14 that chopped up into lots of 24s. And that's what they were trying to do, just pop out 24s and 23s and 22s in different places, trying to make this all work. Whereas I suggested maybe coming in from the other side, trying to set the AS path pre-plan properly so the majority of the traffic comes in through the dual OC3 connection, and then massaging things thereafter. I want to try and get the AS path lengths looking all the same, apart from the biggest path. Step 3, now they actually should go and look at the addressing plan. I mean, if a lot of static customers have already been numbered without really much strategy, then it can be a bit difficult to do. But if it's early days yet, or if it's mostly aggregation pools, say dial or broadband and so forth, then renumbering people is actually pretty easy. So the customer in the vicinities of routers A, C, and D can then be addressed from a contiguous address block assigned to each router. Because they've got 3 major sites and they had 3 exit points, it makes sense to try and keep the traffic that goes to one location using the external links in that location rather than transiting the internal backbone. It's another situation here where the internal backbone is almost as big as the external links, but not quite. So even if you've got 2 OC3s coming into this router C, there's no guarantee there's going to be 2 OC3s from C across to A. Okay, it wasn't anything like that at all. So you've got to try and keep incoming traffic coming into the location that it's finally going to go to. So announcements from the router A address block are sent out to AS120 and 130. Announcements from the C address block are sent out to 140 and 150. And announcements from the D address block are sent from 160 and 170. Note, we're still sending our aggregates, and we've fixed up the prepends. Right? So the aggregates and the prepends are all fixed up. Now we're actually going to subdivide the address space. But rather than just doing a random chop through /24s, we're going to subdivide it into sort of regional address blocks. That's why I say try and do the addressing plan within the network so you can do it on a per region basis. Okay, so picture could be something like this. So we've got router A addressing zone, router C addressing zone, router D addressing zone. Okay, trying to get somewhere close to that. It may not be completely realistic for some people, but as a first step, it's actually quite a good first step to take. And then look at the customer type. In their case, they had 2 types of customers. They had commercial customers and they had consumer. And the consumer access was always about 3 to 4 times the bandwidth needs of the commercial customers, which is actually quite handy because if you think of the math, what 3 times a T3 is an STM1 or OC3. So that was actually pretty handy. So what we do is we announce all the commercial address block, if you like, on the T3 links, and we announce the consumer address blocks on the STM1 links. Okay, that's that. Again, we took the address block to the region. And these guys had a /14, so the address blocks were big ones. They weren't hitting into any of the registry minimum allocation sizes. So we can number from commercial from one address block in the zone and the consumers from the other address block in the zone. Okay, and if consumers ended up using too much bandwidth in any particular zone, then you can maybe take a little bit of the pool from the commercial bit, and so some of the consumer customers would use the commercial bandwidth that it was available. Things like that. It's amazing what you can do with addressing plans just to aid with load balancing. Okay, so I've changed this example from the real life. So I've said, let's say we've got a /16. So router A zone, we make the /18, router C zone, it's a /17, router D zone, it's a /18. Commercial has that /19, consumer has that /19, and commercial for router C zone is the 128.0/18, consumers 192.0/18. Same with the router D zone. We split up the address blocks within the actual backbone. And so router A is going to announce, well, 100.10/16 with a 3 times AS path prepen, because that's just how far AS120 and 130 are. And we're going to announce 110/19 to AS130. So if we look back, 110/19 is the commercial, and 110.32/19, which is the consumer, out to AS120. Router B, which is the exchange point, we just send our address block, we don't care. Router C, we send our address block, that's our big fat pipe. AS150 has got the 128/18, which was the commercial, and 192/18. AS140, that's the dual OC3, that's our consumer. And router D, we do the 3 times AS path prepen for our aggregate, and AS170 and 160 have the same split. Now the reason I'm announcing aggregate out of each path is if router C breaks or the uplinks to either of the ASs on router C break, then we get back up through router A and router D. Okay, that's the reason I'm doing it like this. So that could be a strategy. And I've left them with this, and they're sort of thinking about it and working on it at the moment. But this is the sort of strategy they can actually try and adopt. Multi-homing is not only about playing around with BGP attributes, it's thinking about the addressing plan within the network. Okay, that can be quite a useful thing to think of. So, summary, it's an example. I'm not saying this is the solution for all multi-homing things, but it's an example. You can start from something like this, if it's possible, and follow this strategy. And as ever, mileage varies depending on the situation. But this was one particular ISP with these bandwidths, with this network setup, wanting to achieve more or less symmetric traffic, balancing commercial and consumer usage. They also, the other thing I did mention, they wanted to ensure that the consumers always had access to bandwidth. They didn't want, the commercials always had access to bandwidth. They didn't want the consumers to completely swamp the network. So by doing the announcements like this, we always made sure that the commercial people had access to the T3s. And even if those C whatevers were completely full up, there's no way that the consumers could actually use the T3s that were saved for the commercials. So they didn't have to do any of this weird quality of service stuff and do wacky configurations and routers and get rate limiters and all the other stuff that we were thinking about. This can be done quite simply just by planning the address space and doing the BGP announcements properly. Okay, 20 minutes. This one I'm not quite sure whether this belongs to the multi-homing presentation tutorial or it should really belong to a BGP troubleshooting tutorial. It's become for me a frequently asked question. I'm not quite sure why. Maybe because we're out of the commercial boom of the internet and we're more sort of the real world of people trying to make money, and money is not so easy to come by. So I've put it into the multi-homing presentation, but it's actually more problem spotting and troubleshooting than really multi-homing. Well, I suppose it's multi-homing as well. And it's about transit and local paths. And a common problem that some people are having these days is trying to separate transit and local traffic from BGP customers. You have a transit provider, they provide internet access for a customer over one path, they provide domestic access for a BGP customer over another path. And this is usually required for commercial reasons. So inter-AS traffic is unmetered, so in other words they have a private peering relationship, so local traffic from one ISP is free for local traffic to the other ISP. Whereas transit traffic is metered. In other words, they can provide internet access for their private peer, or a backup, or maybe a main link. That's seems to me a reasonably common situation. The picture could be something like this. It could be over an exchange point, or it could be a private peer, it doesn't really matter. AS110 is a transit provider, but peers domestic routes with other providers, e.g. AS120 at the exchange point. So you see what's happening here? AS120, all the outbound traffic, well, outbound local traffic they want to send across the exchange point to AS110. The internet traffic they want to send over the private wire between routers A and Z. So outbound is dead easy, which is why I haven't put it here, because router A only needs to send a default route to AS120, and that sends all internet. That means all internet traffic will go out to AS110. And router B only needs to send local prefixes from AS110 to router Y, and then we get all local traffic going out across the exchange. So that way is easy. It's the other direction which is not easy. These routers can't inspect packets and check source addresses. Well, they can, but this starts getting into really convoluted configuration. So what you want to do is figure out how to do the return path. Traffic coming in from the internet, which is going to AS120, they want to go over the private link between A and Z. Whereas local traffic, they want to go over B to Y, so private peering traffic. Well, we assume router X announcing 192.168/16, make up a number. Router C and D are those two back there. D is probably just the local router. C is the upstream, uplink. So router C and D will see two entries for IBGP for the 192.168/16. Okay? And BGP path selection will just pick whichever's the best one, probably the highest next hop address, because everything else is important. So it could be router A, it could be router B. You don't have any exit path selection, it's dependent on an IP address. which is not really a very nice situation to be in. Remember from the past selection, you prefer to control where traffic goes rather than being dependent on an address. So there are a few solutions to this. A lot of people just do, well, we can do policy routing. We look at the source address of all the IP packets and we just send them to interface depending on whatever. Sure, yeah, you can do that. That works fine. There's no real big issue with that. I've seen some people put in GRE tunnels and try and send all the traffic over GRE tunnels, and that starts getting very scary. But it works. My preference, as ever with any of these things, is to try and keep it simple. It just needs a minor redesign and the use of a BGP weight. If you remember, BGP weight is not really an attribute, but it's like a local preference. A local preference only applies to the local router. And it's quite handy for a situation like this. The main use of weight in the last few years has been for the reverse path forwarding check in multihoming situations. But this is the other use of the weight. And I've used it like this many times to great effect. So you need a minor redesign, which, well, if it's not acceptable to some people, then, well, there's not much you can do about it. But if this redesign is acceptable, then you can solve this problem just by using BGP. If you move the private peering link to your actual border router, to your upstream router like that, then you can actually make this work quite nicely. Okay, so the private peering traffic will come over the B to Y connection, and the traffic from the internet will come over the C to Z connection. Okay, so let's look at it. Router B, which is that one there, the exchange point router. Here's the 192.168 from router Y across the exchange. Router C, here's 192.168 from router Z across the private peering link. Router B sends it by IBGP to router C, so router C will see an IBGP entry, and it will see an EBGP entry. Best path is EBGP, because external is preferred over internal. So that looks good. So internet traffic coming into router C will go over the private connection to router Z. Wonderful, it works. But router D, here's the prefix of IBGP from both router B and C. BGP best path selection can pick either address depending on IBGP metric, next hop address, and so forth. So it could be router B or router C as the exit point there. That's not so good. You don't want that. Okay. So the way you fix this is say, okay, all the prefixes are here from the exchange point. I'll set a high local preference. Okay, so you set the high local preference, and then on router B. So if you go to router D, you see 192.168 with local preference 100. So that comes from the EBGP with AS120. And then you see local preference 120, where you headed from router B. So that means that traffic from AS110 going across to AS120 will now follow the local preference. In other words, go to the exchange point router B. But the problem here is that local preference is visible on router C as well. So router C now sees that the best path is through the exchange point. Okay, so the internet traffic, rather than going off the private link, now wanders over the backbone and goes to the exchange point. So you've just undone the good that you did. The solution is to use the BGP weight on router C. So the prefix is heard from AS120. That's the first line there. The next hop 10157. Local preference 100, but we've jacked the weight up. Default weight's 32768. If we make the weight 5000, that's higher. That becomes preferred, and it overrides the local preference of 120. Okay? So that way, traffic coming in from the internet will go out through router C to router Z, AS120, whereas the rest of the network, rest of AS110, here's the local preference is 120 is the best path, and we'll use the exchange point connection. And that's pretty much the way you fix that. And that's without using any wacky configurations and so forth. So the transit customer private peering connects to the border router. If that's acceptable, that's fine. Local traffic on the exchange point peering router gets high local preference. Internet return traffic goes on the private interconnect. Domestic return traffic crosses the exchange point. What happens if the private peering link breaks? Traffic backs up across the exchange point. What happens if the exchange point breaks? Traffic backs up across the private peering. Ordinarily, I'd have said that's no big issue. And when I said that to these people who are looking for the solution to this problem, they said, oh, no, we can't do that, we can't do that. The exchange point forbids us to send transit traffic across. I was like, well, how are they going to look? You're going to sit there with a sniffer. Well, we can't tell you. And what about, well, what if the exchange point breaks or the peering breaks? Don't you want it to run over the private peering link? Oh, no, we bill that. And they'll refuse to pay us any money if that happens. So it comes down to money thing, which I didn't really see much issue with. Surely the billing could have been suspended during a backup situation like this. Because it's very rare for things to actually break, but it's quite nice to have the backup if something does. But anyway, if they don't want to have backup, in other words, the exchange point actively does not allow transit, whatever that means, ISP solution, well, you can use communities to help you here. The 192.168 heard via the exchange point, you put in one community, heard via the private peering link, you put in another community, and then set up your IBGP to only send prefixes based on community. So IBGP and exchange point router won't send the 192.168 to the upstream, and vice versa. Therefore, router C only hears 192.168 from the private peering. So internet traffic comes in, router C, it only hears 192.168 on the private connection, so it goes straight to AS120 as intended. If the AS120 link breaks, we don't hear 192.168 of the private peering. We don't hear it from AS110 at all, so BGP backup on the upstream, sorry, the other network AS120 uses their own internet connections backup. Okay. So, like that. So if the link from C to Z breaks, then router C doesn't hear 192.168 anymore, and the backup is run through the whole internet. Which is what these people want. It's like, wait, don't you want to provide backup across the exchange point peering? No, we can't do that. So it's like, okay, do it that way, and you lose the money. Because they could charge what traffic was coming in anyway on the router C connection for this particular customer. It would just mean that it was transiting the exchange point. Anyway, with this solution, breakage in the exchange means the local peering traffic will still back up with the peering link. And this link may be metered and the whole billing issue and all the rest. Because there's a huge volume of local traffic compared with international traffic. So the AS110 solution, router C does not announce the 192.168/16 but IBGP to other routers for the AS110. So if the exchange point breaks, there's no route to AS120. Okay. Unless router C is announcing the default route, which can happen as well. And there you just need to, it just gets hassly. Traffic will go to router C anyway if you've got the default, and you'll need to use policy-based routing to try and fix all that. Because the default route says you know how to get to the whole internet, so you kind of defeat what you're trying to achieve. Okay, so that's the situation. If the link through the exchange point breaks, router C is announcing the default route into the rest of the network. The rest of the network is still going to be able to get to AS120 because router C is sending in the default. So this might be one situation where carrying a default within your own backbone is not a wonderful idea. So you will need to carry a full routing table within AS110 to do that. So it can get a little bit difficult. This way you have to think a little bit more. But I generally find this whole non-backup thing a little bit strange. I much prefer the backup exists for the rare situations where a link like this could break. I mean, in this particular case, I didn't see their infrastructure being that unreliable or anything, but they were quite adamant that they didn't want any BGP backup, which just made the whole thing harder. Okay, so as I say, it rapidly gets messy. The previous two scenarios are quite often requests because it's billing seems to be more important than providing connectivity. But as I say, thinking through the steps, trying to think through what's going to happen, looking at the situation, you usually try and come up with something before having to resort to some really extreme measures. Avoiding backbone hijack. Again, this should probably belong to troubleshooting. I think we've got some slides about this in troubleshooting, but it comes up in so many multi-homing situations. I get asked so often when I do these sort of presentations that I should probably just put it in. And this can happen when peering ISPs are present at two or more exchanges or have two or more private peering links. It usually goes undetected because very few people will sit and look at the traffic flows through the network. Yes, NetFlow has only been around since 1996, by the way. It's very easy to spot with the flow monitoring tools, but I don't know, some people don't tend to look for that kind of thing. And it's usually done because their backbone is cheaper than mine. It could be some funny billing model, or maybe one ISP finds it very difficult or expensive to provide their own backbone with big bandwidth, so they just point a default route or point a route for other parts of the backbone out to their border router and to their neighbor. So it'd be something like this. Router X wanting to get to router Y, we just point a default, well, point a route for whatever's connected to Y out through to router C. Router C hears the prefixes of router Y through B, so traffic carries on like that. That's happened more than once, and I've been asked to help with this more than once, so thought I should probably put it in here. That's why I said a way back that private peering routes should only carry the prefixes we want a private peer to hear and be able to reach. So when AS120 points a static route for an AS120 destination to AS110, the peering routers have no destination. Okay, you only on your own route, you only should be carrying the prefix here from AS110. That's all you should have. Don't carry a full routing table. Carry your own prefixes, of course, but try not to carry prefixes you've learned from your peer at another location. Okay. So what will happen in this case, if you set this up properly, don't put a default route on there, is that the packet comes in, it sees that the best path is actually back the way it came in, so all the happiness traffic will oscillate back and forth and stop. If AS120 points a static route for a non-AS110 destination, the peering routers have no destination at all, so the packet is actually dropped, or the packet flow is dropped. So it's such a simple way of trying to avoid the hijack, but this is why I'm sort of emphasizing when you do this private peering thing or exchange point peering thing, if you don't want your bandwidth to be abused by your peers, then be careful how you configure the routers. Put on only as much information as you want the other people to be able to use. Same applies for private peering scenarios. It's the same thing, but only carry the prefixes being exchanged in the peering. What if AS110 is providing the full routing table to AS120? Well, 110 is now the transit provider for 120. That gets a bit more interesting. So AS120 deliberately uses 110's path. So again, you go from router X through to C to B, back through to Y. So router C is carrying the full routing table, so we can't use the earlier trick of only carrying 110 prefixes. What about using RPF? Well, RPF only checks the source address. It doesn't check the destination. And the source address is fine, because the packets have come in from the network that's originating, and then it goes back through the interface and come in, so that's all okay. But BGP wait is quite handy here. Remember the BGP wait is used to separate local and transit in the previous example? Well, if all the prefixes learned from 120 on router C had a local weight increased, then the destination is back out the incoming interface. So the packets arrive in, see the local weight as something high, says, oh, the destination is back the way that way, so the packets head back. So you get the same situation. You're using BGP to block what's an attempted backbone hijack. And you can do the same on router B. That works quite sweetly also. There are two examples of many possible scenarios. I'm asked these questions all the time, and I'm trying to document them more and more now. It seems to be more of an issue. I've never really seen it pop up as an issue on ISP, BGP, or even on the NANOG mailing list, or even within the NANOG community, but it seems to be popping up in so many other communities I participate in. So maybe people are watching the dollars and cents a lot more than they have done in the past. Or maybe people are getting more aware of the cost of international bandwidth and so forth. And the solution is usually a lot simpler than people imagine. BGP wait, bit of selective redesign of the network. Be careful with how you do IBGP. Yes, IBGP has to be full mesh or using route reflectors, but it doesn't mean you have to announce every single prefix. You can miss out prefix announcements in different parts of the network. Okay, and that works quite nicely. I have 2 minutes, 3 minutes. Well, let's look at communities, just quickly. RFC 1998, that's pretty old now, documented what Internet MCI did with the multi-homing customers. Basically defined these communities. AS number :100 was preferred route, AS number :90, and so on. If you as a customer sent these communities to MCI, they would modify the local preference on their BGP speaking routers to suit. So if they had a prefix with a particular community, say AS whatever :80, they would set the local preference on that prefix down to 80. And so forth. So just looking at the configuration. The whole point about this was to try and simplify the BGP configuration, give the customers control. So the customer could just be told to send particular communities to do particular things. Now, rather than wandering through the whole RFC 1998 configuration, which takes time, or even looking at this, which takes more time, just a real live example. What I want to show you is some of the service provider communities that ISPs have set up. The thing with RFC 1998 is quite a nice idea, but it documented what one ISP did. Some ISPs have copied them and used the same ideas. In fact, in some sense, that the 70, 80, and 90 community numbers have become more or less standard for a lot of ISPs, which is, I suppose, quite nice. That at least it doesn't give surprises for customers. But every network's different, and every network has their own needs, and of course, every ISP has come up with their own community policy. The whole idea being to give customer more policy control, so it's less time for the customer phoning for support, less time to have, less need to have BGP clever people sitting at the help desk and so forth. There are no recommended ISP BGP communities, apart from RFC 1998. That's not even recommended, it's just an informational RFC that a lot of people use. There are the 4 standard communities, the predefined ones, which IANA list. Efforts have been made to document them. I see most recently, I think it was discussed at GROW, maybe last year, was it? Early last year, they discussed something about trying to document communities in use, but these guys wrote something back in, it was like 2001 or something, about trying to document some of the commonly used communities. It made its way to 00 draft, and that's as far as it got, and there's been nothing else really since. If ISPs have got community policies, they usually publish those on a website. So here's an example. What Sprint do, so that's on their website. I only put in as much as I could fit, which is probably completely illegible at the back of the screen, back of the room anyway. That's an example of different communities. You can send these communities to Sprint as part of your BGP session, and they will do particular things. So if I read some out, if you look down the third block, resulting AS path to AS whatever in Europe, if you send 65054 : AS number, we'll do a 4 times prepend of 1239 and so forth. So that's the sort of thing, if you want to massage your own load sharing with SprintLink and other service providers, you can send these communities to do that type of thing. Look on their website, they've got a whole long pages and pages there. Connect to COM-AU. Well, that's what the WHOIS object says on their own routing registry, which is slightly at variance with what they say on their public web pages, but that's why I put both up there. But again, we can do a similar thing. So the customers of ConnectCom in Australia can do this. MCI in Europe, or UUNet of old, they've updated this quite recently. So you can see they support the 72:80 from RFC 1998, and they do the reverse as well. So you can make it more important than anything else here with local pref 120. You can limit announcements, 72:20:30, and then 1, 2, and 3 does the prepends, 1, 2, and 3. Then they've got various other ones that to chop the rest out, just for the sake of space. Okay, so that's the sort of thing that MCI does, offers in Europe. I have no idea if 701 or 73 does something similar, but that's certainly what they do in Europe. BT Ignite, it's European backbone. This changes every time I look at it. So wonderful examples there. You should go and have a look at the WHOIS object, the routing registry. Carrier 1, another one, level 3. I couldn't even begin to explain what all these do, but level 3. But the point of putting these up just before I finish is so you can see what other ISPs have done. So if you find communities interesting to try and help you for multi-homing, or if it helps your multi-homing with your upstream, or maybe you want some policy for your customers, have a look at these, because they're all pretty good examples of what you can possibly do. I have no time for the case study, I'm sorry about that. It's in the slides here. So if you have any, I'll have a read over it. Any questions, feel free to drop me an email. Oops, where am I going? And page up. The slides are there. They're on the NANOG website, the meeting website. That is it. Thank you very much for listening. If you have any questions, feel free to ask afterwards. I'll be here until Thursday, end of the hour meeting, so if you won't have any questions, don't hesitate. Thank you very much.